Yes, right. Someone quickly share rotational motion past paper page through PDF. If you have, share it. If you have, share it quickly in the group. Rotational motion possible discussion quickly. Right, quickly share. Share it quickly. Right, share it quickly. Right, right. Share it quickly. Page through PDF. Page through PDF. Page through PDF. Quickly. 8:35. 8:35. I want to do a proper plan. I will give every month now. I will give the proper plan. Proper plan I will give you, and we didn't have time to give. Right, very busy with the classes and others all. Then Thursday we discussed the rotational motion and hydrostatic fluid dynamics possible essay question discussion. Yesterday, quick revision about rotational motion and simple harmonic motion, but we have a small pending section to be covered in simple harmonic motion. Today we will do that. Today, past paper discussion, MCQ. And tomorrow, model paper writing, target paper, I think 7. It's an essay paper. Come and write the papers. And also, your corrected papers. Your corrected papers will be posted with this May class tudes. May class tudes, right? Your corrected papers also will be posted to the May class tude, right? So then you can refer the mistakes that you have done in your past papers, previous target papers, right? It's a very big process. Ne? But we'll do our best for the 6 months. I will give a plan, monthly plan. This month, this is what I'm going to do. And also Tuesday. Keep in mind, Tuesday we are covering 5 practicals. Now I bring 26 batch theory class also and 25 revision. Then I'm doing unit 2 mechanics 5 practicals quickly. I'm revising. If you really want to do the practicals, if you do really want to do the practicals physically, Tuesday I'm doing an online session to discuss the theory points and everything in practicals. I will arrange Sundays, Saturdays, next Sunday, Saturdays. You can come and you can do the practicals in Vellavata Bambalapeti, right? So I will arrange that facility also. Normally in my classes, we do the practicals experimentally. I have bought all the equipments regarding the practicals. If you really want to do the practicals by yourself, then Saturdays and Sundays, come to the Masters Academy, well, the Vatta, then you can do the practicals there, right? Anyways, Tuesday, we are doing 5 practicals, right? Time is 8:40. Time is 8:40. Okay, right. If anyone has the latest version of Pesuru, if you have the latest version of Pesuru, that means now Pranali shared a PDF in the group. That is what I also have. That is what I also have. If anyone have the latest version, that means I mean this one. I think there are MCQs until 2015 or 16. If you have MCQs until 2021, 22, please share. Please share. If you have, share it. If you have, share it. Otherwise, we'll go to the rotational motion discussion. Rotational motion discussion. Discussion. Right. Past paper discussion. We'll start at 8:40 because no mode of starting. Shall we go and sleep again? Hands up. Who want to go and sleep again? Hands up. Raise your hands. We'll go and sleep. We'll go and sleep. No one. You guys don't have to sleep. You guys don't have to sleep. So you all want to study? Okay. Then I'm the only one who really want to sleep. Right. Okay. Rotational motion. I'll do my best and we'll cover all the issues, solve the questions today. How many questions? Oh God, there are 36. Oh God, 40. Around 40 questions. Right, 1990, 2020, 2017, something. Right. Won't start. Okay. Right. Start. We'll start. We'll start. Quick revision. Quick revision. Quick revision. Can't hear. Quick revision. Quick revision. Quick revision. So not quick revision, past paper discussion, PPT. Past paper discussion, PPT. PPT, rotational motion. Rotational motion. Right. Okay. Right. We'll try to discuss at least 25 MCQs within 2 hours. We'll give a try. We'll give a try. Right. Now keep your focus until the break. No matter, keep your focus. Early morning, we can keep the focus normally. Early in the morning, we can keep the focus. Right. Right. Okay. Okay. Right. Question number three. Question number three. The product of 1998 A level. 1998. Question number three. 1998 A level. Question number three. The product of angular acceleration into time has the dimensions of now angular acceleration into time dimensions. Angular acceleration is alpha. Last we learned into time. Dimensions of angular acceleration into time. Right. Now, angular acceleration means what? Angular acceleration means, we can remember last day I told you, angular acceleration means, okay, angular velocity means, we know omega means theta over t, right? Angular velocity means theta over t. Now, what are the dimensions of angular velocity? Dimensions of angular velocity will be, right? Keep in your mind, omega dimensions will be dimensions of theta over t, right? But we all know that theta is an angular displacement. Angle does not have any dimensions. Time has a dimension capital T. Time has a dimension capital T, right? So 1 over capital T. So then 1 over capital T means T minus 1, right? Then what is the dimensions of angular acceleration? Angular acceleration equation last day we learned. Acceleration means omega over T, if not delta omega over delta T, right? If you subject what is the dimensions of angular acceleration then? Right now, last day I discussed the theory points, but when I am discussing today, past discussion also, you can learn some important theories. Angular acceleration dimensions, we know that dimensions of angular velocity, just now I found capital T minus dimensions of time is what? Capital T. Angular velocity dimension is capital T minus 1. Dimensions of time is capital T, right? That means T to the power minus 2. T to the power minus 2, right? But they're asking angular acceleration into time dimension. Acceleration dimension is just now I found alpha means t minus 2. Dimensions of time means capital T. My answer is t minus 1. So then very clear t minus 1 means dimensions of angular velocity. But let's see what is the answer given in the question. The product of angular acceleration into time has the dimensions of angular displacement means theta. Wrong. Angular displacement does not have any dimensions. Wrong. Second one, angular velocity. Yes. Angular velocity, second one. Yes. No need to look at the other answers. Angular velocity. Right. Okay. Now, additionally, also I will tell you. I will tell you. Torque, moment of inertia, work. So you all know what are the dimensions of work, even though it's a linear motion work or rotational motion work. The dimensions of work will be ml square t minus 2. Right. Now, torque means what? Force into displacement. I told you, torque means force into perpendicular distance. The dimensions of torque also ml squared minus t minus 2. Write down these stories. Huh? But moment of inertia dimensions. Moment of inertia dimensions, you know that. Take one of the example. We talked about lots of examples for moment of inertia. Right? Just take about a point mass mr squared. Mr squared means mass into radius squared. M means capital M. Radius means L. Ml squared. Dimensions of moment of inertia ml squared. Answer is second one. Question number 3, answer is 2. Right. Answer 2. Next one. Uh, question number 2. We'll do question number 3. Question number 3. What they asked in third one. Third one. Third one is not third one. Second one. Rotating flywheel. Kind of wheel. Rotating flywheel of moment of inertia. I. 2 kgm squared. 2 kgm squared about its axis brought to rest in 20 seconds by a constant couple of 20 newton meter acting on the wheel, right? Understand the initial angular velocity of the wheel, in radian per second, right? Now yesterday I revised the theory, today we can do questions. 1997 A level. 1997 A level, next one. 1997 A level story, right? Question number 2. Given data, there is a flywheel. Actually, I want to find the initial angular velocity of the flywheel. I want to find the initial angular velocity. I want to find omega naught actually. I want to find omega naught only. But we understand this one's angular velocity. The speed is decreasing and finally its speed is 0. Final angular velocity is 0 rad per second. Final angular velocity is 0 rad per second. Right? So then we understand clockwise direction, angular velocity decreases. That means this flywheel is undergoing kind of angular deceleration. So same story. Then if I ask you, right, clockwise direction, angular velocity decreases means clockwise direction, angular deceleration. That means there is a torque because we know that in order to change the angular velocity, now let's say there's an object, its velocity is decreasing. Well, object's velocity decreasing means the reason is there should be an opposite force. If the object is going this direction, if you notice velocity is decreasing 5 ms minus 1, 4, 3, 2, 1 ms minus 1, that has a force acting opposite direction. Right? Then this direction deceleration, this direction deceleration, this direction acceleration. Story many times explained. The same story. Now clockwise direction angular velocity decreasing, that means there must be a resultant torque acting on anti-clockwise direction. There must be a resultant torque acting on anti-clockwise direction. There must be resultant torque. Right? Right? Let's say the then clockwise direction, angular deceleration. Anti-clockwise direction, there is an angular acceleration. Anti-clockwise direction, there's an angular acceleration. Think similar way like linear motions. Right? Okay, moment of inertia I is given data. Tau is also given, I is also given. The given data, I given, then time taken. The time taken to move from here to here, 20 seconds. This time is given as 20 seconds, right? I know, we know time, okay? And then what can we do? You know the torque. Now I want to find omega naught, right? I want to apply angular motion equation. Right? How can I do this one? Look here. Now, last time we learned that the resultant torque is tau, corresponding acceleration alpha. Then we learn an equation, tau equals I alpha equation. We can apply tau equals I alpha equation. So when you apply tau equals I alpha equation, the resultant torque, what direction? Resultant torque is anti-clockwise. Resultant torque value is how much? It's 20. Resultant torque 20, moment of inertia 2. Resultant torque 20, right? Moment of inertia is it's 2. Then you can find the corresponding angular acceleration. If I apply tau equals I alpha in anti-clockwise direction, you can find the alpha easily. Then your alpha is how much? Angular acceleration. Anti-clockwise direction, angular acceleration how much? It's just in. If you don't understand, ask some questions in your chat box. in rate per square second. But we want to find out alpha. I want to find omega naught. What can I do? I can consider angular motion equations. I know omega naught initial angular velocity. I want to find final angular velocity is 0. Time I know. Just now I found the angular acceleration. The best angular motion equation will be omega equals omega naught plus alpha t. Omega equals omega naught plus alpha t. Clock in the direction of rotation. Clockwise, I'm applying omega equals omega naught plus alpha t. Right? Then I want to find omega is 0. Omega 0. Look here, omega 0. I want to find omega naught only. I want to find omega naught only. Uh, Alpha. Alpha means acceleration, angular acceleration. I applied clockwise direction, this small equation, but angular acceleration is anti-clockwise. Clockwise deceleration. Anti-clockwise only angular acceleration. So therefore I'm putting minus 10. I'm putting minus 10. Time taken is how much? Simple T is 20. I think simple T is 20. If I'm wrong, tell me. Simple T is 20. Simple T 20. Simple T 20. Am I correct, right? I think I'm right. Simple T is 20. So therefore, when you substitute omega naught, your omega naught will be 200 rad per second. 200 rad per second. Omega naught. Your omega naught will be 200 rad per second. Right. Story is done. Question 2, questions done. Next one. Next one, what? Next one. Right. Right. Look here. Now, question number 4, 1998 A level. 1998, question number 4. 1998, question number 4. I raise this board. Right. Okay, what they are saying. Right. Now they are saying the question. Stars may be formed when a huge rotating masses contract to small volumes. Stars. That means that's star in the sky, I think. Stars may be formed when huge rotating masses contract to a small volumes. In such a contraction, how will the moment of inertia and the angular velocity of the rotating mass change? Right? For our understanding, I'll draw a star. Look here. Now star is contracting just before star, and if I draw after star, right? There's a star. You guys agree, right? This is the, let's say, this is the axis of rotation for an example. This is the axis of rotation of the star just before, right? After, if I do the just after scenario, if I do the star, after scenario, if I do the star is contracted. Its volume is decreased just after, right? I say just before contracting, we know that the mass distribution from the axis of rotation to the mass distribution from the axis of rotation is very high. I will tell you, sometimes you're not very familiar. So what do you mean by the mass distribution? I will tell you, don't worry. Okay. Let's say just before the contraction, angular velocity of the star is omega 1, just after it's omega 2, right? Okay. Now, who plays here? Now you want to understand that conservation of angular momentum stories there. Conservation of angular momentum stories there, right? Okay. Now, I told you moment of inertia depends on some factors: mass, radius, axis of rotation, and also mass distribution. What do you mean by the mass distribution? Mass distribution means from the axis of rotation. From the axis of rotation, when you consider the last particle of the object from the axis of rotation, the particle which is much away, the particle which is at the far distance from the axis of rotation, that length you can say. Right? So then you know that this star's mass distribution has spread until here from the axis of rotation. This star's mass distribution has spread until here. But when you consider this star's mass distribution from the axis of rotation spread only until here. So then very clear, this one's mass distribution has spread to a wide area, wide length, but this star's mass distribution has spread to a low area. Then larger mass distribution means keep in your mind large inertia. Smaller mass distribution means keep in your mind small inertia. Right now, if I hold my hands, if I just if I keep my hands in this way, and if I stretch my hands like this, then we know that my mass distribution is larger from my if I'm rotating the from my axis of rotation from my axis of rotation from my axis of rotation when I stretch my hands, the mass distribution to my particles are larger. In that case, we know that my moment of inertia is larger. When I keep my hands in this way, right? Then we know that my mass distribution is not larger, somewhat smaller, right? That's the story, right? Now you know what is mass distribution. So then we know that during the star contracting, when the star is contracting, what will happen for moment of inertia? The star is contracting, what will happen for the moment of inertia? We know that moment of inertia will decrease. No doubt, moment of inertia decreases. I hope you understand. Moment of inertia decreases. Then there is another theory point we learned last day. There is another theory point we learned last day. What is that? I told you that, like in linear motion, when there is any resultant force acting on a system, its linear momentum remains constant. Now, in this scenario also, there is a resultant torque. Now the star is rotating around this axis, but there isn't any resultant torque acting on the system, right? Resultant torque is zero. In that case, I told you, in a system, in a rotating object, if the resultant torque is zero, I taught you its angular momentum. Its angular momentum throughout the motion. Its angular momentum throughout the motion should be constant. Angular momentum throughout the motion should be constant. That means before angular momentum must be equal to after angular momentum. That means I told you before angular momentum is L1 means after angular momentum is L2. Right? L2. Right. So we know angular momentum should be constant. Last day we learned the equation for angular momentum. We learned three equations. Angular momentum equation is we all can remember L equals I omega. L equals I omega. Before the scenario and after scenario, L value is same. If L is 5, after also L is 5. But we noticed what happened to the I when you consider from before to after during the contraction. We noticed I decreases. L is constant. So you want to ensure L constant. We noticed I is decreasing. When I decreases, what would happen for the omega? What would happen for the omega? Omega must increase. Angular velocity should increase to maintain L constant. When I decreasing, to maintain L constant throughout the motion, angular velocity should be increased. Omega increases. So very clear, this is the story. This is the story. When moment of inertia decreases, angular velocity increases. Angular velocity increases. Right. Omega increases. Right. Right. That means, so when I stretch my hands and when I rotate, my angular speed is less. But when I hold my, when I keep my hands like this and when I rotate, my angular velocity is large. That is the idea. Right. Question number 4, what is the answer? Decreases and increases. Second one. Fourth one, answer is second one. Fourth one, answer second one. Fourth one, answer is second one. Fourth one, answer second one. Right. Fourth one, answer second one. Learn from the questions. Everything is explaining properly. Right. I will like to explain much more, but no time. No time. This time you want to do something. You want to do a game this time. Right. 5, 6, 1998. Okay. 5 is very similar to question number 2. That's fine. 5, 1998 level. 1998 level. 1998 level. Always come, always join live classes. Don't try to watch recordings, especially revision classes. Right. Revision and paper classes. Question number 5. 5, they are saying what? 5, they are saying wheel rotating at a speed of 60 revolution per minute. I taught you how to convert revolution per minute to radian per second. I taught you yesterday. Yesterday, everything I taught. Means yesterday, that 2 hours is more than enough to understand anything. Any level of question, whatever the paper, to score, to do the question, that knowledge is more than enough. Right. There's a wheel rotating at speed 60 revolution per minute. Its axis comes to rest in 20 seconds. Same story. So what is omega naught? Initial angular velocity omega naught is how much? Omega naught is 600 revolution per minute. 600 revolution per minute. Right? 600 revolution per minute. Uh, finally, 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 it comes to rest. It comes to rest. That means final angular velocity is 0. Have they given the time duration? Time duration given as 20 seconds. Within 20 seconds, it becomes 0. Right, becomes 0. They're asking then if angular velocity decreases means clockwise direction, there is angular deceleration. Then where is your angular acceleration? Angular acceleration acting on anti-clockwise direction. Angular acceleration acting anti-clockwise direction. Angular acceleration is acting anti-clockwise direction. Then the resultant torque is acting anti-clockwise direction. We know that in this case, resultant torque is acting in anti-clockwise direction. If the torque is acting in clockwise direction, what will happen? Angular velocity should increase. But since angular velocity decreases, the torque is acting in the anti-clockwise direction, if not opposite to the motion. Right. So what you want to do? This is easy. You want to find the alpha, you want to find the retardation, angular deceleration, that is equal to angular acceleration, only direction is different. So we can use angular motion equation, omega equals omega naught plus alpha t. Very simple. So you guys keep on doing, omega equals omega naught plus alpha t. Right. So angular motion equation. I apply always angular motion equation in the direction of rotation. Disk is rotating in clockwise. Therefore, omega equals omega naught plus alpha t. Final angular velocity is 0. Initial angular velocity omega naught is, that is 600 something. 600 revolution per minute. How do you convert radian per second? Revolution per minute. If you want to convert radian per second, I told you want to multiply by revolution per minute. If you want to convert to radian per second, I told you want to multiply by 2 pi over 60. If you can remember, you should remember. Yesterday night only we learned. Then write. Then what? Okay, then minus alpha is angular acceleration anti-clockwise direction. So therefore it's minus. I want to find alpha only. Time taken. Time taken is simple t is 20. Simple t is 20. Simple t is how much? Simple t in the question how much? Simple t is how much? Simple t given as 20. See how these questions are easy. Simple t is 20. Right. Did they ask us to consider pi as, okay, answer is given in pi. Final answers are given in pi. They are easy. When you substitute alpha. When you substitute our alpha will be how much? Alpha will be, I can cancel out these stories. Then here it's 10, it's 20 pi. 20 pi. Somehow alpha will be 5. Am I correct? This is 20 pi. Alpha will be 5 rad per square second. Rad per square second. I think this is the answer. If I did any mistake, tell me. Fifth one is the fourth one is the answer. Question number 5, answer is 4. Question number 5, answer is 4. Answer is 4. Right? Next one. The sixth one. What they asking? Sixth one, angular velocity has a dimensions of. That is easy. Just now I told you. Angular velocity dimensions. Omega dimension is what? T minus 1. 1999, sixth one. 1999, sixth one. 1999 A level. Question number 6. Question number sixth one. What is the answer? It's T minus 1. Angular velocity dimension is T minus 1. Answer is second one. Answer is second one. Next one is question number 7. Angular momentum. Right. So they have given 3 statements. We'll try to understand what is the correct one. Seventh one, angular momentum statements. Uh, 1999 A level 7-1. 1999. 1999 A level question number 7. There are three statements A, B, C. There are three statements A, B, C. We'll try to understand the correct stories. A, B, C. Right. Statement A. Angular momentum of system. Last day we have an idea what is angular momentum. In linear motion, it is linear momentum. Always compare angular momentum and linear momentum together. So then you can get the right idea. Okay. Statement A says that conserved only when the resultant force on it is zero. Angular momentum of a system conserved only when the resultant force on it is zero. That's telling in a system, in order to consider, in order to consider angular momentum in a system, in order to consider angular momentum of the system is zero. Sorry. In order to consider angular momentum of system is constant. The requirement they are telling the resultant force is zero, right? But we learned the resultant torque should be zero. The resultant torque, if the resultant torque acting on an object is zero only, if the resultant torque acting on a system is zero only, we can say that the total angular momentum of system is zero. If the resultant torque is zero only, total angular momentum of the system is zero, right? Then statement A is wrong. Okay, we'll see. Capital B statement. In the same direction as its angular velocity. I told you in linear momentum also, we know that linear momentum direction is always in the direction of velocity. In angular motions also, angular momentum direction is in the direction of angular velocity. Therefore, statement B is correct. Statement C, independent of mass distribution of the system. Independent of mass distribution of the system. Angular momentum of a system, angular momentum of a system, independent of the mass distribution of the system. Right. We know that. Look here. Look here. Right. That's wrong. Because L equals I omega, L equals I omega. Statement A, I think wrong. Statement A is wrong because they should tell resultant torque is zero. So therefore, I'm putting statement A as wrong. Statement B is, I think, correct. Statement B is correct. B says what? Because direction of angular momentum is in the direction of angular velocity. It's correct. How do you find the angular momentum direction? Right hand rule. Right hand rule. I told you. Yesterday I told you. Now C statement says that independent from the now, C statement is look. C statement is wrong. Okay, angular momentum of system independent of the mass distribution system. That's wrong because L is equal to I omega. L equals I omega. L equals I omega. Right? If you rotate a system with if the system has different moment of inertia, then L is going to change. So therefore, actually, angular momentum depends on the moment of inertia. So this is something equivalent to in linear motion, linear momentum independent from the mass. Wrong. Linear momentum, it depends on the mass. Larger the mass, then your linear momentum also can change. So therefore, we'll consider C also wrong. C also wrong. Therefore, right answer is I say only. Are the answer only B? Only B is the answer. I think only B is the answer. Question number 2. 7 answer is 2. 7 answer is 2. Right. Up to now, story is clear answer. Up to now, stories, everything is very clear. We have discussed, I think, 1, 2, 3, 4, 5, 6 MCQs. Story is clear answer. Up to now, story is clear. Up to now, story is very clear answer. Up to now, if you understand the stories, if you understand the stories, uh, raise your hands. Right. Okay. Next. Quickly. 8:30, 8:40 started. Time is 9. Time is time is 9:10. That means half an hour finished. Right. Right. 7 discussed. Uh 7 discussed. Mm, right. Okay. Question number 9. Question number 9. We'll do ninth one. Ninth one. Ninth one. 2000 A level. 2000 A level. Question number 9. Right. 2011. 9th one. Right. What they're asking flywheel of moment of inertia 9. I means 9 kgm squared about its perpendicular axis through the center is connected to a motor. The motor accelerates the flywheel from rest to 600 revolution per minute, neglecting the friction work, neglecting friction, the work done on the flywheel, the work done on the flywheel, the work done on the flywheel, right? There is a flywheel. That's a flywheel. Motor is connected to a flywheel. Okay, this is a flywheel. Let's see, it's rotating in clockwise or what direction? Initial angular velocity is 0. Am I correct? Flywheel moment of inertia rotates over perpendicular axis through the center. Accelerate flywheel from rest. So now you connect a motor. Actually, this motor is only giving the what? Giving the required. This motor is only giving the required what? Giving the required torque. Because we know that initial angular velocity is 0, its angular velocity increases. Its omega increases means there should be, if omega changes means we know that there must be a torque acting on the flywheel. Then who is going to provide that torque? That torque is provided by this motor capital M. This torque is going to provide by the motor capital M. Right. Finally, it's obtaining an angular velocity. It's obtaining angular velocity how much? 600 revolution per minute. 600 revolution per minute. Okay, 600 revolution per minute. If not, you can write on RPM. Right. Done. Understand. Okay. Right. So they are asking us to find the work done. Rotational work done means you can remember. Rotational work done, we learned. Rotational work done, we learned that. Now they have given I. Given data, moment of inertia given. We know I. I want to find the rotational work done. Rotational work done. How can I find this one? How can I find this one? I know I. I know initial angular velocity is 0. I know final angular velocity. Right. How can I find the neglecting the friction work done on the flywheel? Worked on the flywheel. Right. Right. Okay. Right. Now, okay. I want to find the work done. Look here. Tau equals I alpha. I think they should have given a time. Someone please check. Is there any data missing in this question? If there are any data missing in this question, motor accelerates the flywheel from rest to 600 revolution per minute. 600 revolution per minute. Within any time is given. What do you say? Have they given any time? Any idea? Any idea? They haven't given. Other questions also no, right? Other questions also no. Uh right. Right, okay. Okay. Give me a second. 2011. 913. I. Motor accelerates flywheel. Rest to 600 revolution. Work done on the flywheel. Work done means we know the equation. Work done means W equals tau theta. W equals tau theta. That's the problem. Worked on the flywheel. Right. Neglecting friction, worked on the flywheel. Give me 1 second. Now, angular velocity increases means there should be a torque acting on the flywheel. There should be a torque acting on the flywheel. There should be a torque. So we can do using work energy principle, right? We can do using energy. Yes. Right. Okay. Yes, correct. Look here. Right. Now, look here. Very good. Thank you. Now here, this is the motor. It is the motor. Then they have given I, right? So we know that initial kinetic energy of the initial rotational kinetic energy of the flywheel is 0. Now final rotational kinetic energy is, we know that omega. Then what we can do? Then what happened actually during this period? This period we noticed kinetic energy increased, rotational kinetic energy increased, right? Rotational kinetic energy increased from 0 to some value. Now I told you in the linear motions also, the change in kinetic energy generally, yeah, not always. In this scenario, the change in kinetic energy is equal to the work done on that object. Likewise, here also we can write down work done on the disk means work done on the flywheel means the change in kinetic energy. The change in kinetic energy. In this scenario, this kinetic energy is rotational kinetic energy. So what you can do now here we can write down final kinetic energy equation. We learned that half I omega square. Rotational kinetic energy equation. We learned that rotational kinetic energy equation is, we know that half I omega square, half I omega squared, right? So then we can write down final kinetic energy half I omega squared. Change in kinetic energy means we know that final kinetic energy E2, initial kinetic energy E1. Change in kinetic energy means we know that E2 minus E1, E2 minus E1, that must be equal to the work done, right? Right. So then E2 means we know that half, E2 means half. I means moment of inertia given as how much? I value how much? I value is given as how much? I value is how much? I value is how much? I value. I value is how much? I value is 9. I value is 9. Half. I value is 9. Half I. Omega squared. Angular velocity. 600 revolution per minute. You want to convert to radian per second. 600 revolution per minute. How do you convert to radian per second? If you want to convert 600 revolution per minute, if you want to convert radian per second, multiply by 2 pi over 60. Multiply by 2 pi over 60, right? Whole squared, right? Whole squared minus 0. So then finally 0 0 cancel out. 60 divide by 60 divide by 6, it's 10. Now 10 into 2 means 20, 25. 25 25 squared 9 over 2, 9 over 2, 20 pi whole square means 400 400 pi squared, 400 pi squared. That means here it's 200, 1800 pi squared something. Are there any answer? 1800 pi squared something joules. Yes, it's a good question. It's a good question. Yeah, change in kinetic energy is equal to work done. That is possible. Right. It's a good question. It's a good question. Question number 9, answer is second one. Question number 9, answer is second one. Right. What else? Next one. Then question number 10. Question number 10. What is the year? Question number 10, the year is 2002 A level. 2002 A level. 2002 A level. Two thousand two A level. Right. Keep your focus. Learn from every question. Learn from every question. That's a good story. That's a good story. Five identical uniform rods of length simple limb, mass simple limb. Identical means made with same material and have same masses. Right. Five identical uniform rods of length simple L and mass simple limb. That means that object is made with same length, right? Look at the diagrams 1, 2, 3, 4, 5. So when you add all the length, simple L, second one also L over 3, L over 3, L over 3 means L, L over 3, L over 3, L over 3 means L, okay, right? Some of which are bend as shown, are rotated from rest about a vertical axis. They are rotating. Rods are accelerated until they reach a final angular speed omega. Initially, all these five objects are at rest. Now they are rotating until the final angular velocity is omega naught. Omega naught. Final angular velocity is omega naught. That means all these are undergoing angular acceleration, right? Fine. Which of the following arrangement requires, the highest energy to attain its final angular speed? Highest energy to attain its final angular speed. Right. Look here. Now I don't need to draw this diagram. No need to draw this diagram. Okay, I will ask some questions. Now you'll answer. Just think about mass distribution. Then think about based on the mass distribution, how moment of inertia, MOI going to change. When MOI is larger, then just imagine what can you say about the force, if not torque, that you should give to that object to rotate based on the moment of inertia. Just imagine what can you say about the energy, what can you say about the force, the required torque to rotate that object. Then based on the force and torque, you can imagine what type of energy you need to rotate that object. Okay, now let's see how many you answer right or wrong. Raise your hands. The right answer. The right answer for question number 10 is first one answer. The right answer is first one answer. The right answer is first one answer. Which object that you want to give a larger energy? Which object to get that omega naught angular velocity? To make omega naught angular velocity, which object that you are rotating harder? Which object you are giving very large energy and you are rotating harder to get the desired omega naught velocity? Raise your hands. Option one. Option one answer. Option one. Option two answer. Option two. Option three. Third one. Fourth one. Fifth one. Right. The story is simple. Just compare any object in there from the axis of rotation. When you think any object, which one has the larger mass distribution? Out of those five objects from the axis of rotation, which object has the larger mass distribution? That belongs to object 5. Why? I will take one. Look here, this one. In this one, if you rotate this object in this way, this is your axis of rotation. See, the mass distribution from the axis of rotation to the last particle is very smaller mass distribution. From the axis of rotation to the particle which is far from the axis of rotation, the mass distribution is very smaller, right? Then next one, next object, something like this. This is your axis of rotation. Mass distribution from the axis of rotation to the last particle far from the axis is what? L over 3. This gap is what? L over 3. Next one. Next one is also what? Next one, if you take something like this, this is L over 3. Sorry, this is L over 3. The entire length is L over 3. Then this gap is L over 6. L over 6. So in this scenario also, mass distribution is from the axis of rotation. Mass distribution has spread for a distance L over 6. This case also same. From the axis of rotation for the last particle, this is the farthest particle. This is the farthest particle from the axis of rotation. The remaining particles are not that much far relative to this particle. This is the particle which is at far, which is at far from the axis of rotation. Then this gap is also how much? This gap is also, we know that it is L over 6, I think, L over 6. And then like based on this, you can come to a conclusion. The larger mass distribution belongs to this object. Its mass has spread a distance L over 2 from the axis of rotation. Its mass distribution has spread a distance L over 2 from the axis of rotation. So therefore, this one has the larger mass distribution. Larger mass distribution means we know that larger moment of inertia. Larger inertia means larger resistance, larger reluctance to rotate. Larger reluctance to rotate, because earlier these are at rest. Larger resistance, larger reluctance to rotate. In that case, you want to provide a larger force. That means larger torque. Larger torque means we know that larger energy. Large energy is the idea. Question number 10, answer is 5. 10th one answer is 5. Question number 10, answer is 5. It's a good question. You can learn something from that question. It's a good question. Right? The break is exactly, we'll take the break at 10:15. We'll take the break at 10:15. Right? Answer is 5. Answer is 5. Right. In that past paper discussions also, we have discussed lots of rotational motion questions. Right? Lots of rotational motion questions, past paper essay discussion on Thursday we have done almost, but still there are many. The pending essay questions in the mechanics is only rotational motion questions. Right. Right. Okay. Next one. Next story. That is done. That is done. Then we'll go to 11th one. 2003 A level. Two uniform rods A and B having same dimension. Two uniform rods A and B having same dimension but made of different materials of densities dA dB. Same dimension means A and B have same length but they are made with different materials. Therefore, densities are different dA dB as shown in the figure. If the rotational kinetic energies of the rods are same, then the ratio angular momentum of A, angular momentum of B, angular momentum of A, angular momentum of B. Right. Rotational kinetic energies are same. They are asking the angular momentum ratio. Right. Look here. Right. Now the story. Question number 11. 2003 A level. 2003 A level. Question number 11. Right. The story. Very carefully listen. Huh? Okay. Right. Uh, right. There are two rods. There are two rods. Right. There are two rods A and B. Same length, same dimensions, but the material different. So therefore, density different. Therefore, mass different. Am I correct? Now if you consider a uniform rod, if this rod rotates around axis passing through the center, what is the equation for moment of inertia? We all can remember 1 over 12 ml square. Mass of the rod is capital M. The length is, if you take capital L, then we know the equation. Capital I, moment of inertia will be 1 over 12. 1 over 12 capital M L square equation. Now that means simply we know that moment of inertia in this scenario, length same. Okay, what I do, volume of this rod is, let's take V. Volume of the rod is capital V. Okay, volume of this rod is capital V. Then same length means this rod also having same volume V. So then mass of this rod means I can write down mass as what? Mass means we know the equation. Mass over volume is density equation. The most popular equation every time we apply this equation. Then mass of this rod means I can write down volume into density. Volume into density. Right. So then I can write down moment of inertia means, keep in your mind, moment of inertia means roughly. Moment of inertia means, okay, 1 over 12. No need to write this equation is also okay. 1 over 12. Mass means volume, density, L squared. So when you compare these two rods A and B, when you compare, we know that volume, length are same. So therefore, you can see moment of inertia directly proportional to the corresponding density. Moment of inertia directly proportional to the density. Am I correct? Directly proportional to the density rho. Right? So then, let's say this one's rod A moment of inertia, let's say I1. Rod B moment of inertia, let's say I2. So you can write down I1 over I2 as what? If not moment of inertia of IA over IB means what? IA over IB means you can write down rho A to rho B. Rho A to rho B. Am I correct? IA to IB, we can write down rho A to rho B. I got this relationship. Now look here. There are two rods, same dimensions. So therefore, If it is a rod rotating around its axis passing to the center, this is the equation for moment of inertia. Then I took a relationship proportionality something like this, and IA to IB ratio, I took it as rho A to rho B ratio. Do you really understand? Do you really understand this IA to IB ratio is equal to rho A to rho B ratio? Hands up. IA to IB, it's equal to rho A to rho B. Hands up. If you really understand, hands up quickly. If you really understand IA to IB, rho A to rho B, hands up. Quickly answer. If you're understanding. You guys understand? Raise your hands. Okay. Right. But they are asking the question something else. The question they are asking something else. They are asking angular momentum of A to angular momentum of B. Angular momentum ratio. But they mention both of them have same kinetic energy. They mention both of them have same kinetic energy. Look here. Look here. Both of them have same kinetic energy. A and B. A and B, same kinetic energy. Look here. A and B, same kinetic energy, EE. Right. So they are angular momentum, let's say LA, angular momentum of B, LB. Kinetic energy equations, we wrote three equations. Kinetic energy means we guys know that kinetic energy means half I omega squared, half I omega squared equation. If not kinetic energy means we wrote another two different ways. Half, sorry, P squared, kinetic energy means L squared over 2 simple, sorry, L squared over 2I. Kinetic energy means we wrote that. Kinetic energy means we wrote that. Rotational kinetic energy equals L squared, angular momentum squared over 2 moment of inertia. Now I'm going to use this equation only. I'm going to use this equation only. Right. This story keep in your mind. Right. Same kinetic energy. I want to find the angular momentum ratio, LA to LB ratio. Look here, IA to IB ratio means we all know that it's rho A to rho B. Rho A to rho B. IA and moment of inertia of A, IA, moment of inertia of B, IB. IA, IB. Right. Easy. Easy. Right. Not difficult, eh? Practice. They can't ask question patterns beyond this. Every year, repeating the previous question, modifying a little bit, and giving as you a new question. That's the story. Right. So then when you apply this equation for A, if you apply this equation for A, so then we know that, look here, kinetic energy of AE, then moment of inertia of A is LA squared. LA squared over 2IA. If you apply for this equation for B, kinetic energy is B. So the kinetic energy of B is E. LB squared over 2IB. You can equal these two. So when you equal these two, we can write down what? We can write down. When you equal these two, we can write down what? Okay, equation 1 and equation 2. Equation 1, equation 2. If you equal these two, 1 equals to LA squared. LA squared over 2IA must be equal to LB squared over 2IB. 2IB. Finally, LA to LB ratio. Finally, LA to LB ratio. That's what I want to find. 2 to cancel out. LA to LB ratio means IA to IB. IA to IB root ni. IA to IB the root. 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 IA to IB ratio we know. IA to IB ratio we found. IA to IB ratio means rho A to rho B. We have a final answer. Final answer is rho A to rho B. If I'm wrong, tell me. Rho A to rho B root. LA to LB ratio means rho A to rho B root. This question. It's a nice question. Nice question. We can learn something. We can learn something from this question. Nice question. So therefore, the right answer. If I did any mistake, tell me because I quickly am doing. I can do mistakes. I'm also human, right? So then the equation will be dA to dB root rho A to rho B. Now they consider density as capital D, but I consider density as rho. Rho A to rho B root means what? Answer is fourth one. Answer is fourth one. Right. Next one. Question number 13, 2005 A level. 2005 A level, question number 13. Stay focused. Two 2013 A level. Question number 13. What they asking? Right. Okay. Next one. Right. Next one. Can't we use I mega, I omega for moi? What do you mean? What do you mean by that? Right. Next one. Uniform circular disk of radius capital R, mass capital M. Uniform circular disk, radius capital R, mass capital M, rotates with a uniform angular speed omega in a horizontal plane about an axis passing through its center perpendicular to its plane. Uniform circular disk. Look here. Uniform circular disk. Rotating about an axis passing through the center perpendicular to the disk. Right. Okay. Right. Mass capital M, radius capital R, radius capital R, mass capital M. Mass capital M, radius capital R. Uniform angular speed omega. Omega. Angular velocity omega. Right. The moment of inertia of the disk above the axis described above is half capital M mass. Yeah, this we learned yesterday. If it is the disk of mass capital M and radius capital R, moment of inertia about an axis passing to the center is what? We learned that half M mass squared only. Yeah, correct. When a ball of clay, mass M over 8 is placed gently on the edge of the disk, and if it sticks, the new angular speed of the disk is right. Easy. Conservation of angular momentum. Conservation of angular momentum. Look here. Now story. This is just before. Just before there is a clay. There's a clay ball. That clay ball mass is M over T, but that clay ball is not rotating. That clay ball is at rest. That clay ball is in the system, but it is at rest. Clay ball is at rest, but the disk is rotating. Just after, just after, just after. Now, when you release this clay ball gently on the disk, and if this ball sticks on the disk, right? If the ball sticks on the disk, it is the ball, huh? It is the ball. Then radius capital R. What will happen now? Since this ball sticks on the disk, actually what's happening, what can you say about the moment of inertia? Earlier there was only one disk rotating. The moment of inertia, let's say I1, moment of inertia about this axis I1. But now, not only the disk is rotating around this axis, but also there's a mass sticked onto this disk. Therefore, this mass also rotating. Then you understand that now moment of inertia of the system above this axis is changing. Now moment of inertia is I2. But we know this scenario, there isn't any resultant torque acting system. There isn't any resultant torque acting system during this scenario. Therefore, the resultant torque acting system is zero. Then we can come to a conclusion. If the resultant torque acting system is zero, always throughout the scenarios, angular momentum must be a constant. Angular momentum must be a constant. That means before angular momentum must be equal to after angular momentum. You can apply conservation of angular momentum comb. You can apply comb. You can apply comb I1 omega 1, I2 omega 2. You can apply conservation of angular momentum. That means I1 omega 1 equals I2 omega 2 equation. Ni I1 omega 1, I1 omega 1 must be equal to I2 omega 2. I2 omega 2. Early moment of inertia means only the disk, because this mass is at rest. So therefore this mass does not have any moment of inertia. All disk is rotating. Disk has a moment of inertia. That is half mr squared. Half mr squared. Omega 1, any data given for omega, any date for given omega what? Have they given anything? Omega, yes, omega. Initial angular velocity is omega. Must be equal to, and now moment of inertia of the system. System means your disk plus ball. Before ball is at rest, no moment of inertia for the ball. Only the disk has the moment of inertia, that is half mr square. Now both are rotating. Both are rotating. If you want to find the total moment of inertia of the system, find the moment of inertia of the disk, that is half mr square. Find the when the ball rotates. When the ball rotates, what is the moment of inertia of this ball around this axis? Then it's a point mass. Mr squared equation. I equals mr squared equation. Mass is m over 8. The radius capital R squared. This is the, if you want now, moment of inertia is not a vector, it's a scalar. So therefore, what you can do, in order to find the total moment of inertia, you can add them. You can add. Last I taught you result moment of inertia into now angular velocity is omega dash. Now angular velocity is omega dash. Simplification is there. Simplification is there. What can we do? What can we do? So now I can cut. Now I can cut all the mr squared terms. Simplification. I can cut all the mr squared terms, right? So then here it's remaining, and also I can cut all the half terms also. If I cut all the half, okay, I can cut half the terms also. I can cut half terms, right? Then here I'm getting omega as what? Omega as what? I'm getting here omega as 9:42 1 hour. 8:40 we started. 9:42 1 hour. I can cut all the half terms also. Then omega equals here 1 plus. If I cut half, 1 plus 1 over 4 omega dash. If I'm wrong, tell me. 1 plus 1 over 4 omega dash. Omega dash. Then here it's 5 over 4. 1 plus 1 over 4 means how much? 5 over 4. This side 4 over 5. Is it 4 over 5 omega? Is it 4 over 5 omega? Is it 4 over 5 omega? Answer is, I think omega dash is 4 over 5 omega. Please check if I'm wrong. Tell me. 4 over 5 omega. Answer is 4 over 5 omega. 4 over 5 omega is your omega dash. Answer is, I think, fourth one something. Hands up. Up to now, story is crystal clear. Hands up. Up to now, story. How many MCQ discussed so far? Rotational motion. Yesterday, full revision. We discussed full revision. We started simple harmonic motion revision also yesterday. Up to now, story. How many MCQs also reply someone? How many MCQs finished? Up to now, everything is very clear. Hands up. Very clear. Very clear. Hands up. Very clear. Hands up. Story is very clear. Hands up. 11 MCQs. We discussed 11 MCQs. Okay, right. The break is at what time? 10:15. Yes, we'll work. Only 1 hour. Uh, right. 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 So a 2-minute break to drink water. 2-minute break to drink water. 2-minute break to drink water. Okay. enroll soon for the May classes, right? Because I'm posting tudes on Monday. Right now, I think there is a free link. I think still people are using. But anyhow, I will check the link also. Yeah, for enroll soon. Yes. Then we'll go to right. Mm, yeah. 27. 2011 A level. 26. 26. 2010 A level. 26. I raised the boat. Did you guys drink water? I give a break to drink the water. Did you guys drink water? 2010 A level. Question number 26. 2010 A level. Question number 26. What they're asking, the question they're asking, if the moment of inertia of an uniform cylindrical rod about the axis A, B, and C shown are IA, IB, and IC respectively, then now you know the idea. Look here. Look here. If I do that cylinder, is your cylinder. Nee, is your cylinder. Right. Okay. Now they define some axis. This axis, I think A. This axis A. If this cylinder rotates around this axis, the cylinder rotates around its axis, moment of inertia will be, let's see, like this. Rotating like this, moment of inertia will be IA. IA. And there is an axis passing through the center of the cylinder, vertical axis, right? When the cylinder rotates around this axis, moment of inertia, IB. IB. There is another vertical axis somewhere here. If this cylinder rotates around this axis, moment of inertia will be IC. Right. The story is very simple. I told you moment of inertia based on the axis of rotation. I told you moment of inertia changes based on the axis of rotation. Mass distribution is different. That's why moment of inertia changes. Right. Now, very simple. Now I know very simple based on the theory revision yesterday and today's stories. Please tell me, larger moment of inertia is IB answer. Out of these three moment of inertias, larger one is IB answer. Larger one is IC answer. Large amount of inertia is IC answer. Larger one is, I think, IC. Why? Look here. When you consider the mass distribution from axis A to the farthest particle from the axis, this is the gap. Very smaller mass distribution. When you consider mass distribution from axis B to the farthest particle, this much or this much. But when you consider the mass distribution from axis C to the farthest particle, this is the gap. Now you can't consider this side. This side gap is smaller. That's obvious. But we are considering the in the system from this axis the farthest particle mass distribution. And very clear, larger mass distribution belongs to IC, smaller mass distribution belongs to IE. If you write the proportionality, your IA is smallest. Then your IB next one, largest one is IC. Largest one is IC. That question is easy. That question is easy. 951. IA, IB, IC. I think that question number 2 is the second one is the answer. Question number 26, answer is second one. Answer is second one. Right. Next one. Next one is 27. 27 year. 2011 level. 2011 level. 2011 A level. Question number 27 then. It's 27. What they ask you? Space shuttle. No, don't need to understand the stories. They tell many stories, but the idea is same. Space shuttle B. Where is B? Right. Of moment of inertia I2, angular speed omega 2. Join smoothly with a space station capital A. Of moment of inertia I1, angular speed omega 1 along the common axis as shown in the figure. Neglect the linear motion of the both objects. The angular speed of the system about the common axis after joining two objects would be. Very simple. Very simple story. Look here. If I draw that diagram just before and just after, from this common axis, okay, right. This is the space station, that is capital A. Moment of inertia of the space station around this axis I what 1, and the corresponding angular velocity is omega 1, I1 omega 1. There is a shuttle. This shuttle moment of inertia of the shuttle is, this is B, what moment of inertia I2. This space shuttle also rotating around this axis. Angular velocity will be what? Omega 2. Your system means this time your system will be capital A and capital B. This is your system. Just before they join. Just before. After they join together, we all know that now they behave as one system. Once this shuttle join with the space station, they join together means now they behave as one system. After they joined, both of them have same angular velocity. That's the important story. After they joined, both of them have same angular velocity. That's the story. Both of them have same angular velocity after they join. After they join, both of them have same angular velocity, right? They join, right? They're asking. I think they're asking what is the now angular velocity something. I think that's what they're asking, right? So now angular velocity, let's mark it as omega something. Now angular velocity of the system. This A and B both rotates under same angular velocity omega. Then what is the total moment of inertia of the system? I1 plus I2. Ni? This one moment of inertia is I1. This one moment of inertia is I2. Total moment of inertia of the system will be I1 plus I2. Right. In this scenario, are there any resultant torque acting on the system? No. No resultant torque. Resultant torque 0 means we know that, as I explained before questions also. Resultant torque 0 means angular momentum is same before and after. Same angular momentum means conservation of angular momentum. Conservation of angular momentum. Conservation of angular momentum. I1 omega 1 equals I2 omega 2. I1 omega 1 equals I2 omega 2. Ni? I1 omega 1, I2 omega 2. Right. I1 omega 1 must be equal to I2 omega 2. Then A and B is your system. Total angular momentum of A, I1 omega 1, I1 omega 1. Total angular momentum of B, I2 omega 2. So then the total angular momentum of the system before they join. This is the common symbols. But in this particular question, before total angular momentum, I1 omega 1 plus I2 omega 2 must be equal to after angular momentum of the system. Total moment of inertia is I1 plus I2, I1 plus I2. Now angular moment, now angular velocity, that is omega. If you subject omega, you will get the answer. You will get the answer as what? You will get your answer as what? I1 omega 1 plus I2 omega 2 story. I1 omega 1, I1 omega 1 plus I2 omega 2 over I1 plus I2. I1 plus I2. Right. What is the answer for question number 27? 27, the answer will be, if I'm wrong, tell me, I1 omega 1, I2 omega 2 plus I1 plus I2 means, I think answer is fourth one. I think answer is fourth one. If I'm wrong, tell me. 27 answer is 4. Right. What is 27? Mm, right. Question number, we'll do 31. We'll do 31. 31 also very same story. 2013 A level. 31. 2013 A level story. Right. 31. 31. 31. Next story is 31. Right. Give me 1 second. 1 second. We'll take the break at 10:15. Question number 31. 31. right? 10, 15, we take the break. 2000 year. What is the year? The year is 2013 A level. 2013 A level. Right. 31. Same story. So I don't want to draw the diagram. I think you can understand the story. I'm not drawing the diagram. You can understand me. They are telling two wheels A and B of machine rotate about a common axis in the same direction with angular speeds omega 1, omega 2. Same story. Same story. Something opposite. Eh? You change this side. Horizontal direction. Same story. All right. Moment of inertia of wheel capital A about the axis of rotation is I1. At that of wheel B is I2. Certain instant, the two wheels are pushed or whatever towards each other until they are firmly pressed and the system rotates with a common angular speed omega without slipping. See figure B, the value of omega is given by. I don't want to do it right. Before total angular momentum of the system is I1 omega 1 plus I2 omega 2 in this question also. After angular momentum, let's say after angular momentum is I1 plus I2 omega. You want to find omega, that means I1 omega 1 plus I2 omega 2 over I1 plus I2. That question is easy. I am not doing that question. Answer for question number 31 is also fourth one. Same question. I think they have asked same question again and again. In the now see in your A levels, they can't ask different questions. Same question they change and they give in your year also. If you really practice this past papers properly and if you go to the exam, easy, easy. 10 o'clock, 10 1, 14 minutes for the break. 14 minutes for the break. Right. Next one. Uh, Next one, any easy one? No easy one. Right. Mm, right. 29. 29. This is what I told you. Now, we apply L equals I omega. Ni. But I told you when I was discussing yesterday also, there was a question. In that question, we want to apply MVR equation. Angular momentum means MVR. Yesterday I told you. Ni. If you don't apply MVR, we can't get the answer. 29. Satellite S moves in a elliptical orbit. Elliptical orbit around the Earth. If the speed of the satellite at point A is V, point A is V, then its speed at point B will be. Then speed at point B will be. Right. Then diagram, anything missing? Diagram, anything missing? MVR. This diagram, I think someone sent another different diagram. If you have a different past paper book, if you have a different past paper book, this MCQ 2012 ALL MCQ, can someone send a different diagram? Can someone send a different diagram quickly? I think one data is missing. I think. Can someone send a different diagram? Can someone send a different diagram? Quickly, quickly, no time. No time. We have to do some questions and we'll take the break also quickly. Diagram, I think one data is missing, I think. Quickly. Quickly. Did someone share the WhatsApp at least? No one. Uh, no one shared. Mm, no one shared. Okay. Right. Fine. Thank you. Right. I think like this only. I think the missing data should be like this. Satellite is moves in an elliptical orbit about the Earth. If the speed of the satellite at point A is v, speed of the satellite at point A is v, right? Okay. Then its speed at point B will be. Then its speed at point B will be. That speed, let's put it as VB. I want to find VB in terms of V. I want to find VB in terms of V. It's rotating, but not in a perfect rotational motion. It's rotating. Okay. Then what we can do here? Yeah, what we can do here? We can apply. Now, during when the satellite rotates in a elliptical path, we know that there isn't any resultant torque acting on the satellite. There isn't any resultant torque acting on the satellite. So therefore, for point A and point B, I can apply uh, conservation of angular momentum. I can apply conservation of angular momentum. There is any resultant torque acting on the satellite at point capital A and B. So therefore, I can apply conservation of angular momentum for point A and B. But normally we are applying conservation of angular momentum means I1 omega 1 equals I to omega 2. This question is somewhat different. This question is somewhat different. Yes, 1 cent. Adani, thank you. Thank you, Brinda, so much. Thank you. It's simple D. Ni. That gap is simple D. This is 4D. This gap is simple D. That is missing. This gap is 4D. And this gap is simple D. Right. Now we can do. So we know that I1 omega 1 equals I to omega 2. If not angular momentum means we learned that MV ni MV1 R1 must be equal to ni angular momentum means MVR. MV1 R1 equals to ni MV1 R1 equals to MV2 R2. This is the equation. Normally we apply I1 omega 1 equals I to omega 2. I1 omega 1 means angular momentum. So we can write angular momentum in different way also. MVR. Okay, MM cancel out. Same mass, same satellite is rotating from A to B. Same mass cancel out. Velocity here is V. We can get the answer. Velocity here is V. Then R1 means this is 4 simple in radius. Velocity at point B means that's what I want to find. VB. Radius D. So when you substitute VB, you get the answer. Your VB as what? Your VB as it's just 4V. VB as what? 4V. 4V. Right. Yeah, VB means what? VB means 4V. That's the question. I think that question is okay. That question is okay. We are applying angular momentum, right? Conservation of angular momentum. That's a story. Okay. Then that is done. Done. So we have around 8 minutes for the break. What else? I think question number 11, question number 28 diagram is wrong. Question number 28 diagram is wrong. Anyone, if someone can send 2011 A level that diagram, we can discuss that also. The diagram is, I think, wrong. I think it's wrong. What else? Okay, we'll do 24. 24. 24. Until can someone send that 2011 diagram? I do question number 24, 2010 A level. 2010 A level. Right. Question number 24. Right. But they're asking two stars A and B, uniform density equal radii. Two stars A and B, uniform density equal radii. You want to assume your stars as a spherical objects. Same radii, uniform density. Okay. Right. Star A having twice the mass of star B, spinning 3 times faster than star B. Spinning 3 times faster than star B. Okay. I draw star A and B. Star A and B. Star A and B. Right. they have given star A having twice the mass of star B. Right. Okay. Look here. We want to assume star A and B as spherical objects. Star A is rotating around this axis. Star B also rotating around this axis. Right. A and B. A, B. We know the radius same. Star A, B, uniform density, equal radius. Radius same. Radius same, RR. Radius same, RR. Radius same, RR. RR. Okay. Right. And star A having twice the mass of star B. Mass of star A, let's say, it's too simple limb. Mass of star B is simple limb. Okay. Star A having twice the mass of star B, spinning 3 times faster than star B. Right? Angular velocity of star A is 3 omega means angular velocity of star B is omega. This is the idea given. They are asking angular momentum ratio. Angular momentum ratio, I want to find LA to LB ratio. LA to LB ratio. LA to LB ratio. Right. Then angular momentum ratio. Right. We know that angular momentum means I omega ni. Angular momentum means we know this equation. L means I omega equation we can remember. L means I omega equation we can remember. Moment of inertia. Look here. Yesterday, what is the value I told you for a sphere? It's 203 mr squared. Moment of inertia for a sphere. Not important to do this question. Someone tell yes. For a sphere, moment of inertia is 203. Is it 203? Reply. For a sphere? Yes, ne? Yes. No need, but we'll do it. Look here. Look here. Moment of inertia of a sphere means we know that. L means 2/3 mass capital M radius capital R squared moment of inertia. I means this one into omega. Right. Then we can consider for both the scenarios mass different ni, omega different ni, radius same. Then you can write down L proportional to angular momentum proportional to what? M and omega. That's it. Then you can write down LA means what? We can write down LA, LA over LB. Directly write down LA over LB means you can write down LA means mass of A. Mass of A is 2 simple limb. Mass of A is 2 simple limb into omega means A is omega means 3 omega over LB means mass of B. Mass of B simple limb. Omega of B is omega. Answer is 6. LA to LB ratio is 6. LA to LB ratio is 6. Solid sphere, it's 2/3. Ne? So 205. 205. Ne? It's 205. Yeah. It's 205, but no need. It's 205, but no need. Ne? Right. Okay. Time is 10:13. How many questions so far? How many questions so far? How many so far? How many so far? Reply questions. How many discussed? Reply how many discussed? How many discussed? Discuss 15. Still 15. Still we 15? I sure? 15. Right. Okay. Up to now, we start the class at 8:40. Then time is 10:15. 8:40, 9, 10:15 means 1 hour and 1 hour and 35 minutes. Hands up, the session is so far, it's very effective. So far, session is very effective. Hands up. Session is very effective so far. Right. So what are we going to do is we are going to take a small break. Okay, we'll take 15-minute break. Come at 10:30. Come at 10:30. Still, again, I'm explaining possible discussion, rotational motion, few more questions, at least 25 MCQs, at least remaining last, yeah, at least 25 MCQs. Then what are we doing is we are doing simple harmonic motion sections, right? Then this week classes almost effective if we do the tomorrow's paper class also properly, right? Take a break and come.
Students, give me another 5 or 6, 7 minutes, right? Definitely, we'll start before 10:40. Give me another 5 or 10 minutes, okay? For a reason. Please tell others also. Right. Right. Until 11:30, we are doing rotational motion questions. 11:30 onwards, we are doing simple harmonic motion. Right. Okay. Next one. Next one, 23, 2010 level. 2010 level question. Question number 23. Right. Okay. We'll discuss. Right. Uh, right. If the angular velocity of an object varies with time as shown in the figure, corresponding variation of angular displacement. They have given omega t graph. You want to convert to theta t graph. Very easy. Very easy. They have given omega t graph, angular velocity time graph. You want to convert it into angular displacement time graph. Right. How we do this? So don't think this as omega and don't think this as theta. Think this as velocity. Think this as displacement. That's it. Right. Just think that this is a VT graph, velocity time graph, VT graph given. You want to convert to ST graph. Think like that. Don't think it's omega and theta. Think velocity V and displacement time. Displacement graph. Velocity V, displacement S graph. VT to ST conversion. Right. I explained in motion graphs, in the revision classes also, VT graph, y-axis velocity, x-axis time, right? VT graph, I told you, how do you convert VT to ST? I told you, if you are converting VT graph to ST graph, I told you, whatever happened to the y-axis, in VT graph should happen to the gradient of ST graph. Why? Because displacement time graph, gradient is the velocity. Whatever happened to the y-axis in VT graph should happen to the gradient in ST graph. That's what I told you. Now see what happened to the y-axis in VT graph. Positive velocity increases. That means positive omega, positive angular velocity increases. Positive velocity increases. Positive angular velocity increases. Then in displacement time graph, gradient is the velocity. We know last day also we learned, right? Displacement time graph, gradient is the velocity. In angular displacement time graph, gradient is angular displacement time graph, gradient is angular displacement time graph. Gradient is what? Gradient is the angular velocity. Angular displacement time graph, gradient is the angular velocity. What happened to the y-axis in omega t graph? Positive omega increases, positive velocity increases. Should happen to the gradient. Then in ST graph, in theta t graph, gradient is the velocity omega. So therefore, positive omega increases means, keep in your mind, positive gradient increases. Keep in your mind, positive omega increases means in ST graph, in theta t graph, positive gradient increases. Positive means I told you it's an acute angle. Acute angle increases. Positive means acute angle increases. Positive gradient increases means acute angle increases. Then if acute angle increases graph. I explained the story. It's explained the story. No difference. Right. Question number 23. I think answer is the fifth one. That is also done. That is also done. Right. I say that whenever you see omega t graph, think as VT. Whenever you see theta t, think as ST. Whenever you see alpha t graph, think as AT. Then you are very fluent in ST, AT graphs, right? Do the same thing. Same thing. No difference. 23 done, 24 discussed. Right. 24 discussed. Right, okay. 21. 21. 21, then 20, yeah? Okay, 20, 21. 20, 21. 2009 A level. 2009 A level, question number 20. What they ask you. What they're asking? They're asking moment of inertia of a certain spinning star. Certain spinning star has dropped 1/3 of its value due to contraction. Before and after, let's say before moment of inertia is I, before moment of inertia of that star is I, now moment of inertia is, I think, I over 3. That's what they are telling. Moment of inertia of a certain spinning star has dropped in 1/3 of its initial value due to due to contraction. Now, please tell me my English right or wrong. Now, the way I understood the question is right or wrong. Please tell me. Moment of inertia of a certain spinning star has dropped in 1/3 of its initial value due to contraction. That means earlier moment of inertia I means now moment of inertia IO3. Is it IO3 correct? Is it IO3 or 2IO3? I don't know. Please someone confirm. If you know English better than me, please someone confirm. I think after moment of inertia is IO3. Someone confirm that, okay? Confirm that. Right. Initial value due to constraint. The ratio new rotational kinetic energy, initial rotational kinetic energy. Right. Right. Okay. Right. Look here. Uh, but we know that stars moment of inertia changes, but there isn't any resultant torque acting the star. If there isn't resultant torque, angular momentum is a constant. Before or after, angular momentum constant. Before or after, angular momentum constant. Right? Look here. Then I'm asking, in order to maintain angular momentum constant. Look here. We know the equation, right? Since there isn't any resultant torque acting the star, before or after, angular momentum must be constant. Angular momentum means we know that I omega equation, angular momentum. I'm asking, right? Same angular momentum ni. Angular momentum is LL. Same angular momentum, right? Then what you can do, when its moment of inertia is I, angular velocity, let's say omega 1, when the moment of inertia is I over 3, angular velocity is omega 2, right? Omega 1, omega 2. So you can write omega 1 in terms of L and I now. If you want, you can write omega 1 in terms of L and I. Shall we write? That's better. That's better. Because when you substitute omega means LOI ni. LOI ni. So then we can write omega 1 as what? Omega 1 means L over I. Angular momentum is L, moment of inertia before is I. After moment of inertia I over 3, angular momentum is L. Omega 2 means L over I. Moment of inertia, sorry, angular momentum is L. Moment of inertia, L over I, omega means L over I means I over 3. 3 L over I. This is the idea. They are asking kinetic energy ratio. They are asking kinetic energy ratio after and before. After and before kinetic energy ratio. New rotational kinetic energy, initial rotational kinetic energy ratio. We know the kinetic energy equation, half I omega square. Kinetic energy equation we all can remember. That is what? Half I omega squared equation. Right. Okay. Now, this is after kinetic energy, let's say E2. After kinetic energy is E2. Before kinetic energy E1. You want to find E2 to E1 ratio. E2 to E1 ratio. So we can write down E2 means what? After kinetic energy, half I omega square. E2 means we all know that. E2 means we all know half after moment of inertia is I over 3. Half I omega squared. Omega squared means omega 2 squared. Omega 2 squared means 3 L over I squared. That means 9 L squared over I squared. I hope you understand what I'm doing. Over E1. E2 to E1. E1 means what? E1 means we all know. E1 means we all know. Kinetic energy initially. Half I omega squared. Half moment of inertia. Moment of inertia is I. Omega squared. Angular velocity omega 1. L over I squared. L squared, I squared. So simply we know that half of cancel out. L squared, I squared, L squared, I squared cancel out. I cancel out. Finally, what is remaining here? The remaining 9 is remaining, 3 is remaining. If I am correct. Then the answer is E to D1 ratio is 3. E to 2 E1 ratio is 3. E to 2 E1 ratio 3. If I'm correct, E to E1 ratio 3. If I'm correct, right? If I'm wrong, tell me. If I'm wrong, tell me. 3. Okay. Then the answer is question number 20. Answer is third one. Question number 20. Answer is third one. Next one. Next one is question number 21. 21. 21. That is also 2009 A-level. 21. 2009 A-level. Question number 21. I'll do the diagram. Right. Okay. Right. So when you read the question, figure shows a uniform square plate. Uniform square plate. Uniform square plate. Right. Which has part XBYA. XBYA. X. This point B. XBYC. XBYC. XBYA. Okay. This is XB. Y. This point is point capital A. This point they marked as point capital C. I understand. Right. Has been removed. That means this cap plate, they have removed this section. XBY section removed, and the remaining is this part, right? If the moment of inertia of the plate around axis perpendicular to plate through point ABC, IA, IB, IC. Look here. Point ABC, point A, point B, point C, they are asking. They are asking when your axis passing through point A perpendicular to the board like this. This is your axis at A. Axis at B, axis at C. If this plate is rotating, if this plate is rotating like this is your axis at ABC. They're asking larger moment of inertia belongs to what axis? Larger moment of inertia belongs to what axis? You want to check the mass distribution. Look here. You want to check the mass distribution. When you consider point C, look here. When you consider point C, right? When you consider point C, right? Look here. Look here. When you consider point C, if you consider the axis passing through point C, axis passing the point C. Okay, look here. You know the story in trigonometry, right angle triangles. In right angle triangles, we all know. Let's say this side is simple A, this side is simple B. You know that in a right angle triangle, definitely hypotenuse must be larger than A or B. In right angle triangles, definitely you know that hypotenuse must be larger than A or B. That story you guys know, huh? Right. If I ask you, what is the point? If you take the axis passing through point C, now this is a very good question, right? Now in here, you could easily determine the uh, moment of inertia, which one is larger. But here it's not easy, right? Just take an axis passing through point C. Axis passing through point C. Just think the largest distance, the particle which is far from point C. Where is the particle which is far from point C? So this corner may be, if one can tell, sir, the largest particle is not this particle. So largest particle, sorry, sir, the farthest particle far from point C is not this one, sir. I think it is this one, no, this one. One can say like that. Am I correct? Look here. If you consider point C, the farthest particle. Look here. The farthest particle, right? When you consider when the axis passing through point C, the farthest particle is x or y. Now this gap same ni. Right angle triangles ni. Right angle triangles ni. This length same. Then this length and this length same. Therefore these two hyperlane is same. When you consider point C, this is the farthest distance to the farthest particle. This is the largest distance to the farthest particle. When you consider point C, largest distance to the farthest particles. So when you consider point B, axis, larger distance to the farthest particle, larger distance to the farthest particle. When you consider point B, the largest distance to the farthest particle will be this one, no. If not, this is same. This one, no. This one. Blue color lines. Right? From that we can say, moment of inertia of IC, moment of inertia of the axis passing through C larger than moment of inertia of the axis passing through BY. For the B, distance small, but for C, farthest particle distance larger. Therefore, IC is larger than IB. You can say when you consider point A, point A farthest. For the point A, farthest particle is this length, this one. Particle C is the farthest particle of point A. Now tell me, from this knowledge, black color hypotenuse, red color hypotenuse, and blue color lines. If you really understood, raise your hands. How many of you say? Raise your hands. How many of you say? Larger moment of inertia is IA answer. Larger moment of inertia is IA answer. Larger moment of inertia is IA answer. It should be IA. Because why? This red color length and this black color length is larger. Large moment of inertia is IA. Smaller one is IB. Right? Hands up who understand the story. Okay, wait. Don't hands up. The smaller one belongs to IB. Then this IC, larger one is IE. Hands up who understand my story, hands up. Story is clear, hands up. Genuinely, the story is clear, hands up. Another half an hour, then we are finishing the story, hands up. Hands up, we are finishing the story, hands up. Right? Now learn like this, huh? Learn like this. Right? Then question number 21, I think answer is IA is largest. Second one is IC. Third one is IB. I think fourth one is the answer. If I'm wrong, tell me. I also can do mistakes, huh? But normally no. Normally I don't do mistakes. Rarely only I do mistakes. Normally. Right. Okay. 21 also done. 21 done. 20 discussed. Then 24. We can discuss this question also. Right. Then some stories are there. Some stories. Okay. 2007. 2007. 2007. 17. Question number 17. Right. Now here, as shown in the figure A, child sitting on a rotating chair. Right. Rotates with a angular speed omega. Child is sitting on a rotating chair. Rotates with an angular speed omega. Right. The moment of inertia of the system. Child with the chair. The moment of inertia of the system with the child around the axis of rotation is 2. I is 2. System. Child with the chair. Total moment of inertia is 2. Right. As shown in the figure B, while rotates, the child catches a thin ring capital B. Catches a thin ring capital B of mass 4 kilogram, diameter 1 meter, diameter 1 meter, diameter 1 meter, right? Which is falling vertically with its plane horizontal and with no angular momentum. Right. Find the angular momentum. Find the angular momentum of the whole system would be. Right. Look here the story. Now, right. Look here. I taught you hollow cylinder. Moment of inertia is mr square, right? Someone confirm. I taught you hollow cylinder moment of inertia mr square. Yes. Someone check. Someone confirm, right? Look at the story. There is a child. There's a child sitting on rotating chair. From this axis, moment of inertia of the system means child with the chair. Moment of inertia given as I mark it as I1 something. I1 moment of inertia I1. Corresponding angular velocity they have given as omega. Omega. Corresponding angular velocity they have given omega. Right. Omega. Right. Then what? And there is a ring also. There's a ring also, but that ring, there's a ring. There's a ring. The ring is at rest. There's a ring. The ring is at rest. At rest. Okay. Right. So now what happens? Now just after, I think child is holding the ring. Just after this child is holding the ring. Holding the ring. This child is holding the ring. If I do the ring, if I draw the ring, is the ring. Is the ring. A child is holding the ring. Holding the ring. Holding from his head or whatever. Ne? Holding from his head or whatever. I don't know. Is this guy circus guy? Before, just after. Before, just after. Axis of rotation. Now angular velocity, I don't know. I say now angular velocity as omega 2. Now angular velocity of the system is omega 2. Now keep in your mind who is the system. System is child, chair, ring. That is your system. Child, chair, ring. That is your system. Child, chair, ring. That is your system. Right. Child, chair, ring. That is your system. Right. Now look at the story very carefully. They are asking us to find omega 2. 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 Right. Omega 2. Omega 2. Right. So give me a few minutes. They are asking us to find omega 2. Right. What we want to do? We want to apply conservation of angular momentum. We want to apply conservation of angular momentum. We want to apply conservation of angular momentum. But in that year, look here. In this year, they have given all for this question. In this year, they have given all for this question. Don't know why. The reason is sometimes they haven't mentioned the moment of inertia of the ring. Right? That's why. They have given all this question. Give me a second. You also do it quickly. Quickly. You guys do it. You guys do it. You guys do it. Right. Okay. Look here the story. If it is a point mass, so if it is a point mass, so hollow cylinder ring. Point mass, hollow cylinder ring. Keep in your mind. Point mass. If it is a hollow cylinder, not solid, hollow cylinder or a ring, they all have same moment of inertia mr squared. They all have same moment of inertia mr squared. Right? They all have same moment of inertia mr squared. Huh? Point mass, hollow cylinder, ring, same moment of inertia mr squared. Now look here, we want to apply conservation of angular momentum before and after. We are assuming this system means child, chair, and ring. Before and after, resultant, no resultant torque, no resultant torque. If no resultant torque means we know that. If no resultant torque means we know what? We know what? We know what? Resultant torque 0 means what? We know that angular momentum is constant before and after. Then before angular momentum is L1, after angular momentum is L2, L1 equals L2. That means I1 before angular momentum L1 is equal to after angular momentum L2. So when you apply conservation of angular momentum, it's a good question. When you apply conservation of angular momentum, right? Total angular momentum before angular momentum, I given as 2. The system's angular momentum given as 2. This ring does not have an angular momentum because why? In the beginning, disk does not rotate. Therefore, disk does not have any angular momentum before. This child and the chair is rotating. Moment of inertia of them is what? I given as I1 given as 2. I1 omega 1 ni. I1 omega 1 equals I to omega 2. I1 omega 1 equals I to omega 2 ni. Story. I1 omega 1 must be equal to I2 omega 2 ni story. Right. Then I1 is to omega angular velocity. It's omega. 2 into omega must be equal to total angular momentum after. Total angular momentum after. Already man with the chair has the angular momentum. Sorry, already man with the chair has the moment of inertia 2 plus. Now this ring also has a moment of inertia. Ring also has a moment of inertia. Moment of inertia of the ring. Moment of inertia of the ring. Moment of inertia of the ring is we can find using I equals mr squared equation. Same story. For a ring, for a hollow cylinder, for a point mass, moment of inertia is I equals mr squared equation. I equals mr squared equation. Right? M means mass of the ring. Have they given the mass? What is the mass of the ring? How much? Mass of the ring is how much? Mass 4 kilogram. Have they given the radius? And 4 kilogram and diameter 1 meter. Diameter 1 meter means radius 0.5 meter. Mr squared, mass 4 kilogram. Radius is 0.5 meter. 0.5 meter means half ni. Half squared. Half squared means you all know 1 over 4. I hope this is the total moment of inertia after the system. 2 means moment of inertia of the child with the chair. Mr squared. Mr squared means this one. Into omega 2. You want to find omega 2 ni? This 4 and 4 cancel out. Then it's 1. 2 plus 1, 3. Then you are getting your omega 2 as 2 omega over 3. 2 omega over 3. Then the answer is, I think, second one is the answer. Second one should be the answer. I hope you understand. Second one should be the answer. That is also done. Right, nice question. I think this exposure, more than enough to catch. If you are covering this using watching recording, you will take me long time. Right, right, okay, done. Right. Okay. Right. Okay, then we'll do, we can do 12 and, we can do 12 and 14. We can do 12, 14. We can do 12, 14. We'll do 12 and 14. 12 and 14. Right. Question number 12. Question number 14. I raise the boat. I raise the boat. We'll spend another maximum 15 to 20 minutes and we'll stop this and we'll start discussing simple harmonic motion past paper discussion along with the pending quick revision. So then unit 2 and unit 3 almost covered everything. Unit 4 also we covered up to some level. Okay. Very effective revision. Okay. Very effective session. I don't know how you guys define this. 2004 A level, question number 12. 2004 A level, question number 12. 2004 for a student who are learning, this is very like a what? A big support. 2000, right? They are asking final angular momentum. What is that? They have asked the final angular momentum. That question. Is it sure? No, right? They are asking final angular momentum, not angular momentum. That's the problem. They are asking the final angular velocity. They should ask a final angular velocity. That's the problem. That's why they gave all. That's why they gave all for that question. That's a mistake. They should. It should be final angular velocity, not momentum. Because you look at the answers, all the answers are in omega. So therefore, that's the mistake, and that's why they gave all for that question. 12, 2004. 12, 2004. Right. 2004 A level. Question number what? Question number 12. 12. Right. Now story. Now story is simple. 3 wheels A, B, and C of the same mass and same external radius. Same mass, same radius. Same mass, same external radius, right? Made out of uniform sheets and uniform sheets of different materials as shown in the figure. Now, this is very important question. You will learn a very important point. that we could not catch in the previous questions. But this question, you will understand a very important point. Okay. Same mass and same external radius are made out of uniform sheets. The different materials as shown in the figure, different materials as shown in the figure, these wheels are released simultaneously from rest from the same height at the top of an inclined plane. The wheels roll down without slipping. The wheels roll down without slipping. The order that they will reach the bottom of the inclined plane as first, second, and third, respectively. Okay, this is a story. Uh, the story. Okay, first of all, I will tell you one point. Now, in this figures, these three objects, A, B, and C, they have same mass. They have same mass, and they have same radius. They have same external radius. They have same mass, same external radius. If I ask you which one has the larger moment of inertia, you will wonder. Which one has the large amount of inertia? You might wonder, so if they have same mass and same radius, then it seems like all of them have the same amount of inertia. That's wrong, right? I will tell you the important point, short note point also. Look here, in a system, look here, I will compare two different stories. Look here, there is a plate. There is a plate, a disc, a disco plate. Can you remember what is the radius? Let's say capital R, radius capital R. Mass of the disc is capital M. Mass of the disc is capital M, right? Capital M. And this is the disc. And I will take a ring. I will take a ring. I'll take a ring. I'll take a ring. It's a ring, right? It's not a disc, huh? It's a ring. It's a ring. It's a ring. Radius capital R. Mass capital M. It's a ring. What is the difference between them? Now, both of them have same mass and same radius. Right, you can remember the moment of inertia equation for disk. Moment of inertia equation for disk is, we know that I equals what? I equals for a disk, moment of inertia will be half mr squared, if I am correct. Moment of inertia of the ring is, we all know that I means mr squared. Now see, moment of inertia of the ring is larger than the moment of inertia of a disk. Why? Even though they have same mass, even though they have same radius, why ring has the large moment of inertia than the disk? Keep in your mind, when the mass, now see, now both of them have same mass, but in the ring, entire mass is concentrated far from the point rotation. Keep in your mind, in the disk, entire mass is uniformly distributed throughout the area of radius r, but in here, entire mass is concentrated far away from the center. Keep in your mind, when the mass distribution is, when the much mass is distributed more and more far, right? In a system, if you notice that more mass is distributed, more mass is concentrated far from the point of rotation, then that one has the what? That one has the large amount of inertia, right? Keep in your mind, if the mass distribution is, if the mass is concentrated much far to the boundary, much far from the point rotation, they have the large amount of inertia. Hands up, do you understand what I'm saying? Do you get what I'm saying? Rather than towards center, if the mass is distributing bit away from the center, more and more away from the center, moment of inertia is high. Hands up, the story, clear hands up, the story. Time, story, clear hands up. The story, clear hands up. The story is clear. And now tell me, look at those two diagrams. Based on this knowledge, look at the diagram, three diagrams. Tell me these two diagrams, which one has the larger moment of inertia? Which one has the large moment of inertia? A or B or C? Put reply larger one first. Reply small moment of inertia. Next. Which one has the large amount of inertia? Which one has the small amount of inertia? Reply everyone. Reply everyone. Which one has the large amount of inertia? Which one has the small amount of inertia? Reply everyone. Quickly. Put in the chat box. Put in the chat box. Put in the chat box. Quickly, put in the chat box. Quickly, put in the chat box. Put in the chat box quickly. Which one is large, which one is small? Everyone put large one, smaller one. Large one, smaller one. Put everyone. Which one has the large amount of inertia? Which one has the small amount of inertia? They're very clear. Very clear. Now see, when you consider A, entire simple limb mass, when you consider A, entire simple limb mass is at the border, at the far point, at the far boundary, right? When you consider simple B, uniformly spread, then A should have the large amount of inertia, B should have the small amount of inertia. And C, most of the mass is at the far boundary, but some in between also. So therefore, C has a moment of inertia in between A and B. Larger one is A, smaller one is larger one is A. Keep in your mind, if I properly order it, large amount of inertia belongs to A. This is important pointer, short note pointer. Large amount of inertia is A, smaller one is B, C is in between. Very good story. Right. Okay. Okay, along with this, how many questions? Tell me. Along with this, how many questions? Right? But they're asking not this one. They're asking something else. I will tell you. Along with question number 12, how many questions we discussed so far today? Quickly. 20. Yeah, great. Oh, wow, great. 20. That's great. Thank God. Thank God. Thank God. On this Tuesday, we are doing the practicals. Huh? Tuesday or Monday, both the days, maybe we are doing it two practicals. Revision class also. Revision class means theory I am doing. The revision class people want to join. Right? Because we're stuck any. You guys don't go and you guys don't see Vesak lanterns. Even you see at night. You guys don't go to see Vesak lanterns early in the morning, right? Right. Okay. Right. Okay. I want to teach you one point. Still, this question is didn't finish it. Okay, I'll finish it. Right. Now, okay. I will tell you one theory point also. Right. One theory point. Right. Right. Okay. Look here. The theory point. Right. The one is having large amount of inertia. Right. The one is having, keep in your mind, the one is having larger moment of inertia. Keep in your mind. Takes larger. No. You know that if you now what is the question? What is the question? The question says that. These fields are released simultaneously from a same height at the top of an inclined plane. Now these two are released at same height at the inclined plane, right? Keep in your mind, the one is having large moment of inertia, coming very slowly. The one is having large amount of inertia, keep in your mind, coming very slowly. I don't derive it. So therefore, where their velocity is small. Large amount of inertia means smaller velocity. Smaller velocity means keep in your mind. They are rotating slowly. Smaller angular velocity. Therefore, they take larger time. Because if your speed is small, to come to a certain distance, you take larger time. Large amount of inertia means smaller velocity, small omega, larger time. Right? Okay, what they're asking. From this knowledge, you can tell. You can tell what? You can tell that this question we can tell 1120. We can tell what? We can tell the order that they will reach the bottom of the inclined plane. The order they reach the bottom. Large amount of inertia takes the larger time. Therefore, larger one comes last. Small amount of inertia will come quickly. Then first two is coming. First, second, and third. First one is B. Second one is C. Third one is A. Am I correct? BCA. BCA. Right. BCA. Right. Hands up. story, right? We discussed 20 MCQs. We'll do the remaining. I think we have around 10 to 12 MCQs. Ni. Remaining we'll do. Don't worry, we'll do. Uh, I want to put a plan. We want to put a plan also. And then we want to increase the duration also. But increase in durations, I also do. I increase the duration like this. Night time. If I'm increasing the duration, it's night time because night time means midnight time. Because you want to now more than enough to study now with the current plan you can study other subjects. Time is more than enough. Please don't tell you guys don't have time, can't manage. I don't know. I'm wondering, can manage, because the parts that you should learn I am doing, past paper discussion I am doing, right? Quick revision I am doing. So therefore while joining to my class you can revise them, but I tell that parallelly if you have a capability of managing two three things together, you can parallelly listen to my explanations and quick revision. Then if you like to do something else, you can parallel, you can do it if you are eligible. If you are not eligible, don't do that. But now in the paper class, ne, you should do your self studies over to do it. I will give the work plan also this week. I will give separately based on your paper marks. I'm continuously I'm tracking your marks. But people who write the paper only, I can give a proper plan also. All right, therefore come and write the paper. Come and write the paper, right? Come and write the paper. I'll give the work plan also. So now in this physics class, you can manage this time. Now we are doing Friday, Saturday, Sunday. We are doing, but you have enough time to cover other subjects also. You have enough time. It's all about how you are managing your time, how long you sleep, at what time you wake up, at what time you sleep, in between, what are you doing? Studying in the sense actually what are you doing? So you are just sitting and you start studying for half an hour. Again, your brother calls and your mother asks you to come and sweep the house. Then you can go and sweep the house. If not, suddenly you take your mobile phone and watching some videos, YouTube videos, some other teachers video. This teacher's video. If not cooking video, if not if not actor videos, sometimes TikTok, and you spend 1 hour and again, oh no, I should not watch videos. I should again come to the track and I want to study again and again studying. After half an hour, again, what are you doing? Okay, right. I'll have a small nap. I'll have a small sleep and I'll come and you go to sleep and you spend another 1.5 hours. You wake up and coming and sitting and studying. There's a problem. There's a problem. And also going so many classes also not a good option. Going so many classes, everywhere classes. Now, you want to select three best classes for each subject. One subject, one class, three best classes. That's the way. That's the way. Going that class, the same subject, many classes, five, six. Some of them do going three classes for same subject. Then it's up to you. It's up to you. It's not the good option. When you go more classes, you don't have time to do that. Go for a one class where they do everything. That's the best option. So then you don't manage the time also, right? So in case if you are increasing the work now with the 6 month, I want to increase the work limit that we are doing, right? But mostly I am taking night times, midnight time is the less efficient time to make it efficient. Let's say now normally if you are studying from early in the morning to let's say you are starting morning 6 a.m. to you are studying until 10 o'clock night, then almost you did your energy, your battery almost has gone, almost gone, right? Then if I put a session 10 to 12:31 for an example, you have to stay somehow if you really want to study. Now if I don't do the session, sometimes you might sleep, right? 10:30 or 11. If I do the session, sometimes because you feel that I want to join the session somehow, even you are tired, you join and you cover it. Then you can further effectively spend that another 2 hours also. So therefore, that's the plan. That is the plan upcoming days. I will give a proper plan. No time to give everything. That's the problem. No time, but I will give a plan also. Currently, I know that this class is going very effective. Our ultimate goal is actually this is a actually paper class for the 25 revision. No, first shy, second shy, third shy, doesn't matter whoever. Why we are doing this class? To do papers, paper writing, paper marking, discussion. That is the ultimate goal of doing this class. But what is the problem? To write the papers, some students they say they can't remember the theory. They say that I learned, but not that much confident about what I learned. Right? So therefore, it's not mandatory. Only ultimate goal is paper writing, paper marking, ranking. Continuously writing papers. That is the paper class. To support you only, a session called quick revision. We are revising theories, everything properly, A to Z. Some kind of additional work. I should not do that work for you. You should do that work somehow. Since you are not doing, I am doing the session. Then what happens? Then okay, quick revision, quick revision. Okay, I revised rotational motion yesterday. Likewise, I am revising the theory sections. Then my goal is to focus you. My goal is to engage you into the papers. But what happens? What happens? You tell that, sir, I know all the theory points as you discuss in the revision class. I know all the theories, but I don't know how to apply in the questions. Yesterday, rotational motion quick revision, everybody explained. Just think, we have discussed 20 years of papers so far, today's session. Other than what I taught you yesterday, within 1.5 hours, I revised everything. Other than what I taught you in yesterday's session, anything, any theory, any difficult theory came out from that? No, right? But what you guys tell, sir, sir, yeah, you taught the quick revision. We know the theories, but the model papers, when we write the papers, we can't get the marks. Now we don't know how to do the question. To support you, right? Okay. You are telling like this, okay? Then we'll do a possible discussion, right? Because we can't do tutored questions. It's a theory class. If you are doing a revision and if you are doing tutored questions, it will be a theory class. Then better you join 2026 and 2027 badges to cover them. Since to make it as a revision, a different scenario, right. Then we'll do a past paper discussion. Then I am discussing all the question patterns, all the questions from 1990 to 2025. Then you can grab all the question patterns, all the stories, how theory is applied in every question. You can get the idea. Today's session, we discussed 20. You understood how they are asking. Now your final goal is, okay, I help you for the revision. I help you for the past paper discussion and question practice. But what is most important is writing papers. But you know what is the problem? The problem is around 50 students they enrolled. Only last week, not last week, target paper 3, only 4 wrote. Target paper 5, only 6 or 7 wrote. 6, 12 wrote. What is the core in this paper class? People, students skip. The core in the paper class, students skip. Students get the remaining. Quick revision and past paper discussion, yeah, they are important. But the most important thing is this paper writing discussion. We are discussing some good questions, not like this. Our paper class questions, you know, very standard questions. But they are skipping that. They are not writing. How pathetic. How pathetic their life, the story. The students thinking how pathetic. That is the problem. So then do you think that now what will happen? Now what will happen now? Okay, I'll talk a little bit. And now a student, let's say, now I'm telling we are doing 25 papers. Come and get the exposure. I'm telling definitely you can go to B. Definitely if you work, you can go to A. No issue. The 6 month more than enough to get A. I am telling like this. I'm telling again and again I'm like this. And students don't come and write the paper. Even they write, they like to do MCQ, they don't like to do essay. Right? Then what will happen? They don't write the paper properly continuously. First week coming, second week absent, third week coming, fourth week absent, fifth week exam, seventh week coming. No use. No use. In the 25 papers, you don't write properly. Then your result is, let's say, see, normally my class, students don't get W. Never got W for physics, as for my knowledge, people who work with me. Normally, my class, rarely only there are S. Normally, C is there. Normally, C there. Is very rarely only. Okay, right. Okay, right. Then what happens? Your result, let's say, for example, 3S. Then what are you doing in your second Shayo, third Shayo, whatever? You are changing the class. No, sir, it's not good. I'm going for another class. That's the thing. We tell to do this one, that one, not following, not following. You know, you always, I know because of your age, I think. Because you are 18 and you are big adults now. You guys don't listen what we say, right? Whatever the plan in your mind, you guys following. And when something goes wrong, you guys don't like to put the blame. You put the blame on your teachers. Now, sir is because sir only. We didn't teach. Now the thing is, some students now, let's say now, if I missed to discuss a small section, let's say a small section, like covered all the syllabus, and let's say I missed a small section, right? That shouldn't go W, but it is telling, sir didn't cover the syllabus. How they put the blame on teachers, huh? Sir didn't cover the syllabus, that's why I got W. This guy, sir has covered 99.9999 theory sections. From that theory knowledge, this guy can't get at least S. At least is he's justifying the reason behind his W is because I didn't cover the syllabus. That's why mama. That's why dada. That's why mother, mom, umma, amma, appa, amma, tata. This is just why I got failed. The mother's fathers also believe what to do. Is the reality of the world, right? Uh, anyways, raise your hand. Session is very effective. Session is very effective answer. Session is very effective so far. Answer. Session is very effective answer. Session is very, very effective answer. Effective. Right. 10, 11:30, 11:30. Won't discuss what simple harmonic motion story. I will stop before 12:30. I will give another break. Normally, I give break. That break when big larger break, 25 minutes. Will take 5 minute break. Oh, come at 11:30, 11:40. Okay, 11:40. Come at 11:40. Yes. Right. Simple harmonic motion pending. Pending revision. Pending revision. I don't explain how every graph comes, but I try my maximum to explain all the necessary points. If I explain, it will take long time. Right. Last day where I stopped in the revision yesterday, in the quick revision, simple harmonic motion, I'll just stop. Definitely class will be finished before 12:30. Class will be finished before 12:30. We start at 8:30, 4 hours. 4 hour session. Right. Then simple harmonic motion. Revision. Look here. Simple harmonic motion revision. Right. The remaining pending revision. Okay. I think I discussed about where did I stop? Where did I stop? At the last. At last, I stopped where? The revision. Give me 1 second. I stopped yesterday. Mm, I showed about how, yeah, force time and acceleration displacement. Force displacement graph varies. I told you story. Right. Also, look here then simple harmonic motion. Just think, just think, quick revision, SHM, simple harmonic motion, part 2. So class will be finished before 12:30, part 2. Right. Right. Okay. Right. After I cover that practicals on this Monday or Tuesday, essay papers, there will be practicals also. Right. Every month we'll plan to do at least 5 practicals. Now there are 38 practicals. Every month we'll do 6 practicals. Then 36, around 36. Every month we'll plan to do 6 practicals per month. Right. Okay. Right. Simply, if there is a simple harmonic motion, if an object moves a simple harmonic motion, look here. The story. Right. This is my equilibrium point capital low, and positive amplitude plus capital A, and negative amplitude minus capital A. The stories, you know the stories now. Positive amplitude, negative amplitude minus capital A. Right. Okay. Right. We know velocity is maximum at the equilibrium point, velocity is zero at the amplitudes. Also we know that kinetic energy is maximum at the amplitudes. Sorry, acceleration is maximum at the amplitudes. Acceleration is maximum at the amplitudes, acceleration is zero at the equilibrium point. Now look here, just think an object moves in a simple harmonic motion. Look here, when this object is moving from negative amplitude to equilibrium point, what will happen? When the object is at the negative amplitude, I told you velocity is zero. Then what will happen? When this object move, velocity is zero. At the negative amplitude, velocity is zero. When this object is going to the equilibrium point, I said the velocity is increasing. At the equilibrium point, we know velocity is maximum. Am I correct? Am I correct? Am I correct? Right? Am I correct? Then what happens? When this object further goes to the right side amplitude, we know at the amplitudes velocity is zero. Then velocity is decreasing. Velocity is decreasing. Velocity decreasing. Velocity is decreasing. At the amplitude, velocity is zero. Then object is returning, changing the direction to the opposite direction. Again, velocity is increasing. Velocity is increasing. Maximum velocity is decreasing. This is what's happening. This is what's happening actually. Velocity is increasing. Right? Velocity is increasing. The same velocity, huh? Same velocities. Velocity is decreasing. Zero. This is the variation of velocity with the motion of simple harmonic motion. Then velocity increasing means kinetic energy increasing. That story, right? So if I do the variation of, keep in your mind, uh, kinetic energy along the displacement. If I do the kinetic energy variation, keep in your mind. If I draw the kinetic energy variation, keep in your mind, y-axis displacement x. Very careful, listen. This is plus capital A. Plus capital A. This one is minus capital A. Minus capital A. Right. Look here. Look here. Story. Very very simple story. Kinetic energy. Look here. We know that velocity is maximum at the equilibrium point. Kinetic energy is maximum at the equilibrium point. Velocity is zero at the amplitudes. Therefore, kinetic energy is zero. Kinetic energy is a scalar. Kinetic energy is a scalar. Therefore, when you draw the kinetic energy graph, you will get something like this. Kinetic energy graph variation like this. Okay. Blue color one is the kinetic energy. Ke. Right. Also, now normally I said that best example for a simple harmonic motion is right motion of a mass connected to a horizontal spring. Motion of a mass connected to a horizontal spring. If you consider kinetic energy variation is like this. If you consider the potential energy variation, if it is a spring, elastic potential energy variation, the variation will be something opposite, right? The potential energy variation will be something opposite to kinetic energy variation. Now you know that in the gravitational field, you know that when this object is falling down, what will happen for the gravitational potential energy? Decreasing. Parallelly, what will happen for the parallelly what will happen for the kinetic energy? Increasing. When potential energy decreases, we know kinetic energy increases. When potential energy decreases, we know kinetic energy increases. The same story here. Kinetic energy increasing means the corresponding energy is potential energy, that is decreasing, right? That is decreasing. This is the when kinetic energy increasing, the potential energy will be decreasing graph. Is the potential energy decreasing graph? Something opposite. And then you can say this story. Kinetic energy maximum at the equilibrium point, then the potential energy is zero. Kinetic energy is zero at the amplitudes, potential energy is maximum. You just write down. I can't give all the points. You write down these points. Huh? Okay, the variation of the total energy. Right, keep in mind the total energy of a system is constant. The total energy of a system is constant when an object moves in simple harmonic motion also, no matter where is the object, the total energy means kinetic energy plus potential energy always a constant. The total energy graph will be a horizontal line graph like this. Potential energy, kinetic energy, this one is the total energy. Total energy graph. Total energy graph, right. What else? What else? That story is done. That story is done. That story is done. What else? The next story. The next story is right. Okay. Now, variation of potential energy with the time, variation of kinetic energy with the time. Think like that. Right. Sometimes still you're not very familiar with this potential energy graph. Therefore, I will take the example motion of an object connected to a horizontal spring, and I will show you story. Look here. No time. That's the problem. So revision. Look here. This story, careful listen. Careful listen story. This story, careful listen. Careful listen, huh? Look here. Right. Initially, there's a spring. The spring is at the natural length. Right. Initially, the spring is connected to a mass, but the spring is at the natural length. If the spring is at the natural length, we all know that is there any elastic potential energy stored in the spring if it is at the natural length? No, no need. Because we know elastic potential energy changes, sorry, elastic potential energy stores when the spring undergoes extension or compression. When spring deforms only, elastic potential stores on the spring, right? Look here, then this point is our equilibrium point. This point is point capital O. This is our equilibrium point, right? So when your spring stretched, when your spring stretched, the next story, the next story, right? Now when the spring is stretched, then there is an elastic potential energy, right? There is no object, extension. That's the displacement, if not extension, simple x, displacement, simple x now. Amplitude is, let's say, somewhere here. Here is our amplitude, capital A, right? What will happen? What will happen when the object is not stretched, when the spring is not stretched, the object is at the equilibrium point. No stretching means potential energy, elastic potential energy is zero. Am I correct? That's why zero. Somewhere here, there is an extension. That means spring is stretched. That means there is elastic potential energy. What is the equation to find the elastic potential energy? Half k squared. We revise histories. Elastic potential energy equation, you all can remember half k squared. Half k squared, half k squared. When x increases, now see, when the object is going this direction, look here, when this object is going from the equilibrium point to right direction, your x is increasing. Your x increasing. Then x increasing means elastic potential energy increasing. That's why, like this. Other negative scenario also you can understand this negative y when object goes towards negative amplitude y, elastic potential energy increases. This story, no compression. Right side extension. When this object is going towards negative amplitude, spring is compressing. When spring compresses also, we all know that. When spring compresses also, we all know that there is a elastic potential energy storing on the spring. Right? Now, when the object is here, negative, this direction displacement x. Then also spring compressing. When spring compresses also, there is a elastic potential energy. Is the idea. That's why the graph. General answer, this graph story is clear answer. This graph story 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 is clear answer. Graph story clear. Right. 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 Next one is okay. Then kinetic energy, potential energy, total energy, variation with the time. With the displacement, kinetic energy variation with the time. Keep in your mind. The y-axis. Now, normally, simple harmonic motion, there are graphs. The kinetic energy variation with the time. Right? Look here. This story. Keep your focus. This story. Right. 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 Now depends on depends on the initial position of this object. Depends on the initial position of this object. This graph can slightly vary. We'll consider when in the beginning, when the time is zero, we'll consider the time is zero. Look here. This object is this horizontal spring is stretched. This horizontal spring is stretched and the object is at the amplitude when the time is zero. Then we know when the object is at the amplitude, the spring is stretched at maximum displacement. So therefore, potential energy is maximum when the time is zero. Am I correct? Then what will happen to the potential energy? Then we know this potential energy is what's happening. Once you release it, what will happen? This object is coming towards the equilibrium point. That means x decreasing. When this object is coming towards the equilibrium point, this x decreasing. X decreasing means elastic potential energy decreasing. In the graph will be elastic potential energy decreasing like this. At the equilibrium point, elastic potential energy is zero. At the equilibrium point, elastic potential energy is zero. Right? Now further, this object is going towards the left side. Passing this equilibrium point, further object is going towards the left side. Again, x increasing. Again, x increasing means elastic potential energy is again increasing. right? Now this is now then object reaches the negative amplitude. Then again coming to the right side. Ne? After obtain the maximum negative amplitude, this object is again coming towards the equilibrium point. Again x decreasing. Again x decreasing means elastic potential is decreasing. Right? Then this object is further going to the right side. Again x increasing. This is how your variation of potential energy graph. Variation of potential energy graph. Right? Based on this graph, you know how to draw your kinetic energy graph. If you have doubts, put your doubts. Huh? If you have doubts, put your doubts. Right? Based on this, you can draw your kinetic energy graph. You can draw your kinetic energy graph. If you draw your kinetic energy graph, okay, kinetic energy graph. Kinetic energy graph. At the positive amplitude, potential energy is maximum. Kinetic energy is zero. Why? Why kinetic energy is zero? At the amplitude, it is released from rest. At the amplitude, it is released from rest. Kinetic energy is zero. When the potential energy is maximum, kinetic energy is zero. Then what happens? Kinetic energy is increasing. Now kinetic energy is increasing. This object is going towards left, velocity is increasing. This object is going towards left, velocity is increasing. Kinetic energy is increasing. Maximum. This object is going from equilibrium point to here, velocity decreasing, kinetic energy decreasing. This object is going towards right, velocity increasing, kinetic energy increasing. Story. Kinetic energy. Total energy. Variation in the time. Total energy variation in the time. Total energy variation in the time. Total energy variation. You know that total energy remains same. Total energy variation is remains same. With the time, total energy must be same. Kinetic energy plus potential energy variation is same. Throughout the graph, the variation will be same. Same variation. Right? Same variation. Right. Same variation. Right. Okay. What else? Then that graph story is done. This is one type of a graph. Another type of graph. Next what? Time is 12 o'clock also. I want to finish before 12:30. I want to finish before 12:30. What else? Graphs. Graph story. Graph story. Okay. Variation of velocity with x. If I draw one oscillation, one cycle, variation of velocity with x. If I draw variation of velocity with x, Vx graph, right? Now you also refer your notes also. Now, not to refer the notes also. I am explaining the points, but like a theory class can't teach you properly in detail exactly what's happening. Can't teach you like in theory class. That's why we are called this as revision class. We are revising. Revising is not learning theories again. Right? Next story. Velocity x graph, Vx graph. Look here, Vx graph. That means when you consider one complete oscillation, one complete cycle, how velocity is varying throughout the what? Throughout the displacement. Your y-axis velocity, right side direction vectors positive, left side direction velocity negative. Positive amplitude, this is negative amplitude. Your x. How are you going to draw it? Look here. Look here. What will happen to the velocity? At the equilibrium point, at the equilibrium point, okay, at the equilibrium point, let's say this object is starting at the equilibrium point and this object is going this direction, again coming to this direction like this. We'll say when the time is t equals 0, object is starting the motion right direction. Thinking that way, no issue. Then at the equilibrium point, velocity is maximum, and velocity is right direction, positive velocity maximum, plus v max, plus v max. I don't know whether this graph is clear. If it is not clear, please tell me. If it is not clear, please tell me. Right? Positive velocity maximum right side direction. What's happening to the velocity? Velocity is decreasing. At the positive amplitude, velocity is 0. At the positive amplitude, velocity is 0. And the graph will be, keep in your mind, This is not a, it's kind of a elliptical one, right? Some kind of elliptical one, right? Then what? Then what? From positive now object is change the direction and again going towards left side. Then velocity is increasing from 0 to maximum. But look here, this time velocity direction left side velocities. Again, positive amplitude to the equilibrium point, velocity left side velocity means negative velocities, like this. Then what? Then further, object is going towards the negative displacement side. Object is going towards the negative displacement side. Left side velocity decreasing. Left side velocity decreasing and becoming 0. And again, object is coming towards right side. Velocity is increasing. Story. This is a graph. Right? Done. Keep in your mind, we know linear velocity means mass and velocity. We all know that linear velocity means important point, mass and velocity. Throughout, when you consider this object mass is same mass, then if they ask you in the exam, velocity variation with the displacement and linear momentum variation, they are same, right? If you draw the linear momentum variation also same manner. Why? Because linear momentum means mass and velocity. Mass is a constant. Like how velocity varies, linear momentum varies. Why? Linear momentum and velocities are vectors. They are behaving very similarly. Story done. Vx graph and I write down this Px graph. Linear momentum displacement graph. Right. This story done. Graph story done. But there are some other graphs also. 12 o'clock. Time is 12 o'clock. Time is 12 o'clock. Some stories I will teach you in the questions. I will teach you reference circular motion. I will teach you what's reference circular motion story. Reference circular motion story. Right. Right. Yes, can't avoid. Okay. Look here. So what is this reference circular motion? Finish, huh? Finished. Story almost finished. What is this reference circular motion? I'll tell you. Look here. Every simple harmonic motion has a reference circular motion. Right? Every simple harmonic motion has a reference circular motion. Reference circular motion. Right. Look here. I will explain that. If I don't explain, then you don't understand. I don't like to explain, but it's okay. I explain briefly. Careful listen. Blue color is the simple harmonic motion. Black color one is reference circular motion. Right. Equilibrium point. Okay. Equilibrium point. Just think when the object is at the positive amplitude, keep in your mind, when the time is t equals 0, keep in your mind, the time is t equals 0, object is at the positive amplitude, right? Just think about the simple harmonic motion of this object. This object is starting the motion from positive amplitude and going towards left side, passes equilibrium point, going towards left side, reaches the negative amplitude, and again changing the direction and going towards the equilibrium point, passing through the equilibrium point and going towards the positive amplitude. Simple harmonic motion. Right. They found that every simple harmonic motion has a reference circular motion. Right. Every simple harmonic motion, they found there's a reference circular motion. Every SHM, there is a reference RCM, reference circular motion. Why? The reason is, so let's say when the object is at point A, the circular motion also object is at point A, right? When the object is somewhere here, keep in your mind, in the circular motion, right? Just imagine, okay, red color dot is circular motion. Blue color one is simple harmonic motion. When the time is A, in the circular motion also, when the time is t equals 0, the time is t equals 0, in circular motion also, object, there's an object, it is at here. So now this blue color object in SHM moving towards this point, moving towards this point. Then in the circular motion, red color object, when this blue color one is going from here to here along the straight line, red color one is moving from here to here, here to here. Red color one is moving from here to here, right? Here to here. Do you understand? So therefore, if I track the circular path, if I track the circular path traveled by the red color one, the circular path, right? Okay. So likewise, when in the simple harmonic motion, the blue color one is somewhere here, right? Be careful, listen. In the circular path, circular motion, red color one will be somewhere here. The circular motion, red color one will be somewhere here, right? Right. Okay. Right. Understand. Your story is understanding, right? Likewise, keep in your mind when this when this blue color one is somewhere here, when the blue color one is at the negative amplitude, the circular motion also red color one is going a half circle and reaches somewhere here. Just somewhere here. Theory class, I take half an hour or 1 hour and explain. Right? Do you understand? Do you understand? Then red color path. Right. Okay. Likewise. So in the simple harmonic motion, now this object is changing direction, moving right side. Moving right side. Then in the reference circular motion, this object will be somewhere here. The reference circular motion, object is somewhere here. Right. Time to stop the class. We want to come to the revision. Right. I can't explain like this. Somehow, keep in your mind, like this. When an object moving in a simple harmonic motion, there is a reference circular motion. Okay, right? When simple harmonic motion completes one cycle, the reference circular motion, the shadow or something completes one cycle. Just think the real object as the object in simple harmonic motion blue. Shadow of the blue color object is red color one. When blue object moves one oscillation in SHM, shadow red color one is also moving one circular motion. So that's the link between simple harmonic motion and circular motion, right? Okay. The important points in simple harmonic motion, the amplitude. Look here. This is the amplitude. This is the amplitude of simple harmonic motion. That is equivalent to the radius of the circular mode. That is equal to the radius of the circular motion. So therefore, the first point is amplitude and radius same. Right? Amplitude is same. Right. Okay. So there are two equations based on the story. There are two equations. Yesterday we learned about instantaneous velocity. We learned maximum velocity. We learned acceleration equations. But today I will teach you there is another equation which gives the relationship between displacement and time. XT equation. Up to now in SHM, we didn't learn any equation give the relationship between x and t, displacement time relationship. We didn't do any equations. Now only we are learning. Look here. Look here. Right? Look here. Right. Okay. That equations are derived. From this reference circular motion and simple harmonic motion connection only. Right. Okay. I can't derive it. If I derive it, we will take so much of time. Can't derive it. I don't derive it. But when you do the question, you understand. Don't worry. Right? Look here. Normally, right? Look here. Important equation. Very, very important equation. Simple harmonic motion. In a simple harmonic motion, right? In a simple harmonic motion, equilibrium point is here. Let's say amplitude is somewhere here. Plus say whatever. When the time is simple t, okay, when the time is simple t, object is somewhere here, displacement is x, time taken is simple t, right? Time taken is simple t. Now I'm going to teach you the relationship which gives the relationship between x and t. The equation which gives the relationship between x and t. Remember, this story is very important, right? So there are two equations which give the relationship between x and t. The first one is x equals a cos omega t. X equals a cos omega t. Another one is there x equals a sine omega t. You must learn by these two equations. Why, sir? There are two equations for x and t. Now, what is the in linear motion? The relationship between a displacement x and time simple t means s equals ut plus half a t squared. But here, why there are two equations? The reason is if the motion, the question they will tell, if the motion when the time is t equals 0, if the motion starts from the amplitude, keep in your mind, if the motion, the simple harmonic motion, if the motion starts from the amplitude, I can't derive those stories, then it will become a theory class. Keep in your mind, uh, if the motion starts from the amplitude, if the motion starts from the amplitude, when t equals 0, when t equals 0, if the object is at the amplitude, you want to use this equation x equals a cos omega t. If they give the time n, if they give omega n, if they give a n, if they are asking a x, if they are asking x, if they mention the question, object starts the motion from the amplitude, it can be positive or negative. If the object starts the motion from the amplitude, this is the equation, right? Okay, learn by heart, learn by heart. In a question, if they tell that when the time is 0, the motion starts from the equilibrium point, equilibrium point, equilibrium point, equilibrium point, equilibrium point. This is the equation x equals a sin omega t, right? uh, can derive it but can't. Revising ni, this is enough to do any question, this knowledge enough to do any question, right? Right, up now story crystal clear answer. Story up to now crystal clear answer. Time is 12:15, maximum 10 minutes. Raise your hand. Story up to now crystal clear answer. Story up to now crystal clear answer. Crystal clear. Crystal clear. Right. Right. 12:15. Right. Uh, almost done. Uh, almost done. Main story is done. Right. Okay. Right. Okay. We'll draw four graphs and we'll finish the revision of simple harmonic motion. This knowledge is more than enough. There's another four graphs. Look here. Right. There's another four graph. Hands up, tired hands up. Feeling tired hands up. Feeling tired hands up. Feeling tired hands up. Yes. What to do? Feeling tired. Okay, fine. Right. Okay, last 10 minutes. Last 10 minutes, we can stop the class and we can go last 10 minutes. Right. Okay. Right. Mm, right. Right. Look here. Okay. Uh, right. Look here. I said one complete oscillation in SHA means if the motion starts somewhere here, the time is t equals 0. If simple harmonic motion starts here, one oscillation in simple harmonic motion means, look here, object, this is your equilibrium point. One, if the motion starts from here, when t equals 0, then object goes towards equilibrium point, passes the equilibrium point, reaches the negative amplitude, turn back, turn back, turn back, reaches the equilibrium point, coming back to the initial point. So this is we call as one oscillation, one simple harmonic motion. This is one simple harmonic motion. Then corresponding circular motion is one complete circular motion. In the reference circular motion, then the corresponding object completes one circular motion. Right, starting from here, coming to here, one circular motion. Then time taken, keep in your mind, the time taken for the simple harmonic motion and the time taken for time period means what? time period means we know that time taken for one oscillation. The time taken for one oscillation in simple harmonic motion and time taken for one circular motion, they are same, right? Time taken, time period are same, time period same, time period same, right? Okay, that means when the time is t equals 0, carefully listen, when the time is t equals 0, right? Object is here. When the time is t over 4, right? The time is t over 4, object is here. Keep in your mind, I don't draw the diagram. The time is t over 4, object is here. When the time is 2t over 4, the time is 2t over 4, object is here. The time is 3t over 4, object is here. The circular motion. 3t over 4, object is here. When one complete time period finishes, again object is here. If you draw the graph, variation of displacement, look here, the last few graphs. Look here, variation of displacement with the time. T over 4. This one is 2t over 4. This one is 3t over 4. 3t over 4. This one is 4t over 4. That means t. Right. Look here. Okay. Look here. In the simple harmonic motion, look here. The simple harmonic motion, equilibrium point, when the time is t equals 0, object is here. Am I correct? When the time is t over 4, object is here. The time is t over 4. The time is 2t over 4, object is at the negative amplitude. When the time is 3t over 4, object is at the equilibrium point. The time is capital T, object is again at the initial point. Right. Right. Look here. This story. Last story. Finished. Finished. We can finish the story. Story finished, huh? Story finished. Finished. The last 3-4 graphs finished. Okay. Look here. Look here. Look here. Look here. Look here. So when the time, look here, I'm asking the displacement. When the time is t equals 0, the time is t equals 0, where is the object? T equals 0, object is at the positive amplitude. Am I correct? Object is at the positive amplitude. Nee, positive amplitude. Right. Okay. Right. When the time is t over 4, object is at the equilibrium point. When the time is 2t over 4, object is at the negative amplitude. Object is at the negative amplitude. Negative amplitude. Right. When the object is 3t over 4, again object is at the equilibrium point, displacement 0. When the time is t, again object is at the positive amplitude. That means somewhere here. If I do the graph, for a one cycle variation of displacement time graph, look here. Hands up, this graph, clear hands up. This graph, clear hands up. Raise your hands. Genuinely hands up, this graph is clear hands up. Genuinely raise your hands. This graph is clear hands up. Genuinely. This graph is clear. This graph is clear. Right. Then velocity. Velocity. Look here. VT graph. Quickly. XT, VT, AT. Okay, VT graph. Next one is VT graph. Next one, VT graph. Right. We'll take this as T over 4. 2T over 4. We'll take this as 3T over 4. This one is capital T. Right, fine. Okay. Simple harmonic motion. Look here, simple harmonic motion. When the time is t equals 0. The time is t equals 0. Object is here. Velocity is 0. When the time is t equals 0, object is here. Velocity is 0. So therefore, t equals 0, velocity is 0. Right. Object is moving to the left side. When the object is at the equilibrium point, velocity is maximum. Velocity is maximum, but velocity is left side direction. When the object is at the equilibrium point, velocity is maximum, left side velocity, negative velocity, negative velocity, negative velocity, negative velocity maximum. And the time is t over 4. Right. Next what? Next what? In the next story, when the time is what? T over 2. This is T over 4. The time is, sorry, 2T over 4. T over 2, 2T over 4. Velocity is again 0. Velocity is again 0. The time is, then changing the direction. When the time is again 3T over 4. Velocity is maximum. Direction, right side direction. Right side direction, velocity maximum. Right side direction, velocity maximum. Finally, when the object is at T, again at the amplitude. At the amplitude means we know velocity is 0. Okay? At the amplitude, velocity is we know it's 0. If you draw the graph, draw the VT graph, look here. The VT graph. AT graph, AT graph. The last two, AT graph, FT graph finished. AT graph, FT graph, section revision finished. AT, FT. Look here. AT was the same story. AT graph, next one. AT graph, next one. AT graph, next one. AT graph. Look here. AT graph. Time is almost 12:30. I want to stop the class also. T over 4, it's 2T over 4. 3T over 4. Then the capital T. Look here. Equilibrium point, positive amplitude, negative amplitude. Right? The time is T equals 0. T equals 0. I told you what? I told you. Acceleration is maximum left side. Why? Always acceleration towards equilibrium point. Always acceleration towards equilibrium point. Left side acceleration. Negative acceleration maximum. Left side acceleration. The time is T equals 0. Negative acceleration maximum. Negative acceleration maximum. Can write down. Negative acceleration maximum. Time is T over 4. When the time is T over 4, object is here. Acceleration at the center is 0. I told you. When the object is at the negative amplitude, acceleration always towards center. Always acceleration towards center. At the amplitude, acceleration is maximum. Right side direction, maximum acceleration. That means the time is 2T over, when the time is 2T over 4, positive acceleration maximum. Right. Plus A max. And the time is 3T over 4. 3T over 4 also. Acceleration 0. The time is capital T. Again, acceleration is left side. Maximum. Acceleration is left side. Maximum. That's it. The graph. Done. Finished. The graph done. Is the graph. Properly draw it. Keep in your mind. Not only acceleration, but also force. Force displacement graph. Force time graph also same. Same graph. Won't teach you about phase story, phase part. When I do questions, I will teach you. Right. Hands up. Hands up. Simple harmonic motion is the oral revision. This is what they are going to ask. When you're doing, we can't do the past of the question today. We can't do the discussion today. So we'll plan on next week. Hands up. Session is fully effective. Everything is very clear. Session effective, hands up. Session effective, hands up. Right. Effective. Right. Okay. The time is 12:23. I think today class is very effective. We have done. Come and write the papers. Then finish. Let's stop the class. Right. Study well. Study well. That's the most important thing. Study well. Don't waste the time. This 6 months, don't waste the time. Right? Even you have 5 minutes to study, please don't waste your time. Study. Right? Today, to get the maximum benefit. Okay, class is finished. Right.